All right, hello and welcome back to Real Seekers. Finally I get to come back to my cosmological argument. So last time I finished part 1 and part 2, which were basically getting into the first premise of our cosmological argument, argument from contingency of the universe itself. And you'll remember last time, so we covered 3 arguments that prove that the universe exists as a contingent thing. So it's not a logically necessary thing that exists. And in part 1, after covering a couple of philosophical arguments or modal type arguments for the contingency of the universe, we then got into the first William Lane Craig philosophical argument that the universe did in fact begin to exist. And if it began to exist, it's not eternal, and therefore it must be contingent, because eternality is a necessary condition for something's being logically necessary. So obviously if it's not eternal, by definition it is a contingent thing. And we covered the first philosophical argument from the impossibility of an actual infinite existing in reality. And then in part 2, we covered the second philosophical argument that was independent of that first philosophical argument, and it argued again for the finitude of the universe, meaning it's not eternal, from the impossibility of forming an actual infinite through successive addition. So it was not necessarily saying that it's impossible for an actual infinite to exist. The second argument says, no, let's pretend you can form that, but you still can't form this particular type of actual infinite, namely one through successive temporal succession, and adding one temporal moment after another and that sort of thing. And it sort of assumed the A theory of time that we went over. This, in part 3, we're going to finish off a third argument from the Kalam cosmological argument based on the science, the field of cosmology proves on a balance of probabilities that the universe very probably began to exist. And this is where we're going to get into the scientific method and that sort of thing. So that's what you have to look forward to in part 3 here. And with part 3, that will finish off our premise 1, the warrant for premise 1 in our argument that the universe is a contingent existing thing. Now, just so you know, probably going to have to break up part 3 into 2 parts, just because there's so much information in establishing this argument from the science of cosmology. So I'm going to have to break it up into 2 parts, 3A and 3B. Then in part 4 we will cover premise 2, which is basically the principle of sufficient reason. Namely, everything that exists has a sufficient explanation of its existence. And then in part 5 we'll finish off the cosmological argument solo series with the warranting the third premise, the most important one, that God is the explanation of the universe and that sort of thing. So that's the plan of action for this upcoming shows on the cosmological argument. As I said, in this part 3A and part 3B, we're going to be finishing off our assessment of premise 1, or providing the warrant from premise 1. And this is an independent argument from the fact that the universe began to exist and is therefore by definition contingent, based on the scientific evidence. So a little bit different from parts 1 and 2, where we looked at deductive philosophical arguments. In this episode, we're going to be making an inductive argument instead, or rather an abductive argument. So that's basically where we're going to be making an inference to the best explanation. So essentially, deductive arguments, basically, given the truth of their premises, they guarantee the truth of their conclusion. It's impossible for the conclusion to be false if the premises are true. The deductive arguments are truth preserving, as philosophers call it. Inductive arguments are more probabilistic, so that it makes the conclusion more probably true than false, and that's all we're trying to do here. In other words, we're trying to make inference to the best explanation, and this is specifically known as abductive, abductive reasoning. And primarily the main difference between an inductive and an abductive argument is that inductive arguments tend to be based on probabilistic inferences based purely on statistical data, and by statistical data in the frequentist sense of the word. So you have what's the probability that you'll roll a 1 if you roll the dice or something like that, or that you'll pick an ace out of the deck or something of 52 cards. Inductive arguments, on the other hand, just to sort of quote an expert in this area who wrote the article on logical inferences, Igor Duvan from the Stanford Encyclopedia of Philosophy, he sort of phrases the difference between inductive and abductive reasoning this way. So, quote unquote, the best way to distinguish between induction and abduction is this. Both are ampliative, meaning that the conclusion goes beyond what is logically contained in the premises, right? So they're not truth-preserving like deductive arguments. But in abduction, there's an implicit or explicit appeal to explanatory considerations, whereas in induction, there's not. With induction, there is only an appeal to observed frequencies or statistics. And that's sort of the main difference with us. With our approach, we're doing an inference to the best explanation, and that's why it's an abductive reasoning. We're looking at explanatory considerations and various cosmological models that might explain the scientific evidence that we have, and assessing those in light of each other, which one of those explanations is the best. Now, one quick note outside of the approach that we're using with this argument in part 3, bear in mind, again, this is an independent argument from both of the philosophical arguments we gave in parts 1 and 2. As well, this argument is time theory independent, so it doesn't matter. B theory of time is true, eternalism, A theory of time is true, or possibilism, some kind of hybrid of the A-B theories of time. Whatever theory of time is true, this argument works and proves that the universe began to exist. So unlike our second philosophical argument that we covered in part 2, it doesn't matter what theory of time is true. This abductive argument that we're giving will work. Okay, so having established our approach is an abductive one here. We want to prove that the model that says, cosmological model that says the universe began to exist is the best explanation, or that we can infer given the scientific data that we have. And so obviously there will be two essential elements here in part 3 for establishing this abductive argument based on the scientific data. So aspect number 1 will be obviously to establish, well, what is the scientific data, or these empirical evidences that we are going to be using to argue that the universe began to exist. And on this front, I'm going to be presenting two main sources of empirical evidences. Again, these come from Dr. William Lane Craig's column Cosmological Argument, when he's establishing premise 2 of the argument that the universe began to exist. And that's going to be, number 1, based on the thermodynamic properties of the universe in light of the Second Law of Thermodynamics. And the second is going to be obviously based on the expansion of the universe. The universe is expanding. Additionally, also we'll have mathematical evidences, so singularity theorems or mathematical proofs that are associated with the evidence for the expansion of the universe, and kind of will be used to hint that the universe did in fact begin to exist. So the second category there includes mathematical theorems and proofs that are associated with the evidence from the expansion of the universe. So those are the two main categories of scientific evidences that we're going to be using to argue in aspect number 2 that, well, the best explanation of this thermodynamic and expansion rate data for the universe is that it must have begun to exist. That's the model that we're going to be trying to argue for, and that's better than any of the eternal cosmological models or explanations that can be offered. Now, in order to help us establish aspect number 2, that the notion that the universe began to exist is better than the others, we're going to be assessing the various cosmological models in light of the best explanation inference criteria, as I call them. It's the BEI criteria, as I call them. So there are 4 ones that I think are really important, and these are going to form the framework of how we assess the various scientific models for the universe. So the first one is going to be plausibility. The second is explanatory scope. The third is based on explanatory power. And then finally, the criterion of simplicity, as it's called in science, or less ad hocness. It has less ad hoc components. And I'm going to assign my typical normative or subjective probability values to each of these factors for all of the cosmological models. You can do your own. You don't have to have the same subjective probability as myself. But then at the end of the day, we're going to see, do my subjective probabilities fall within the reasonableness range, and how do the various cosmological models stack up to each other based on these subjective probability values in light of these best explanation inference criteria. So that's the framework of what we're going to be doing in this show. And just to sort of give you an idea, well, what are these best explanation inference criteria, or BEI criteria, that you're using, these 4 essential elements? So in the first place, what does it mean for a model to be plausible? Well, basically we're just saying that the hypothesis must be implied by, the truth of the model is implied by, or at the very least it is consistent with, to a greater degree, and by a greater number of other accepted facts or truths. So in philosophy we call this our background knowledge. It's consistent with, or even better, it's the truth of the model is implied by our background knowledge to a greater degree than the other hypotheses or the other cosmological models. So really, in other words, this criterion really assesses whether our areas of knowledge that are known with confidence outside of the area of study, do they support and or suggest the truth of a given hypothesis? A part of this is going to employ the scientific principle of falsification, which is a form of reasoning known as denying the consequent, right? So if a model is true, it predicts various things, certain things that we should see. Does that obtain or not? If something that a model predicts is falsified, meaning it's not true, the consequent is false or denied, then that must mean that that model is automatically false. We know that it can't be true. So that's what plausibility is about, just to give you sort of a general sense of what we'll be looking at there. With explanatory scope, this criterion really accounts for the quantity of the scientific facts that can be accounted for by our given hypothesis or cosmological model. Obviously, the greater number of facts that a model explains, the greater explanatory scope that model has compared to other models. Explanatory power, for me, this is the most important one, but it looks at the quality of the explanation in relation to explaining the facts. How well does it actually explain the facts? And the hypothesis or the model that explains the scientific data with the least amount of effort, or lacks vagueness or ambiguity, that is the theory that has the greatest explanatory power. So if you think of explanatory scope and power as putting like a puzzle together, explanatory scope would be the greater amount of pieces you put together is the greater hypothesis, whereas explanatory power is, well, sure, maybe someone has got all the pieces put together, but he had to force them. They're not in the proper pieces that are put together there. He's put one piece that's supposed to be in a different spot together with another piece that they're not meant to be. In that case, it would have a greater explanatory scope if he's managed to put every piece of the puzzle together, but he would lack explanatory power because he's putting the wrong pieces and forcing them to fit together rather than putting the natural pieces that are meant to fit together in place. So that's a way to, that jigsaw puzzle analogy comes from Mike Lacona's book, so that's a great way of visualizing those criteria. And finally, we have the less ad hoc, or the scientific criterion of simplicity, or sometimes it's called maximum parsimony, or ceteris paribus in Latin, if you want to get fancy. But yeah, basically the hypothesis or the scientific model that employs the least amount of ad hoc components. So ad hoc, it's Latin, it just means for this, it's an unproven assumption or a non-evidenced assumption that has to be made in order to make the hypothesis work. So obviously the superior model or hypothesis of the universe will be the one that employs the least amount of these ad hoc components. Sometimes in science this will be referred to as Occam's razor. You might have heard that in scientific disciplines. So the simplest hypothesis, or the most elegant hypothesis, is the one that's to be preferred. Those are our four criteria that we'll be using to make an inference to the best explanation. However, one thing that I think is really important here, and I'm just going to do this simplistically, but right out of the gate, it could be possible that we find the cosmological model that is the best explanation. Let's pretend I prove any models that say that the universe began to exist are better on these four criteria, inference criteria, compared to any eternal cosmological models. Well, that doesn't necessarily mean that it's true. The best model may only have a 36% probability of actually being true. Well, that's not the best explanation. There's another explanation. The unknown eternal cosmological model might be much better. It might have a 64% probability of being true. Something else other than that. So in this case, I'm assigning a significance weight to the four inference criteria in terms of how well these inference criteria allow us to assign an actual truth value to the model, to the best model that wins out based on these four criteria. And I would say I'm at least 85% certain that these criteria, based on their track record, the hypotheses that are less ad hoc or simple, hypotheses that have great explanatory power and explanatory scope, and that are plausible, tend to be true and are proven to be true given the fact that they're the best at fulfilling these criteria. So that's sort of the significance weight that I'm giving as a multiplier to multiply to the probability that any given model, the best model, fulfills these explanations to the best degree. Just be aware that there is that significance issue of, okay, great, it fulfills these criteria, but then so what? What's the significance of that in terms of proving that the model is in fact actually true? And I've assigned this subjective probability of 85% that these four criteria I'm using as my framework provide us with that. We can be confident that the model that fulfills these four criteria to the best degree is probably true in reality. Okay, so with that said, let's move straight into the argument. So let's provide the warrant for this first aspect of our abductive argument here, namely establishing the truth of these two major scientific or empirical evidences that we have. And on that front, the first one that I wanted to look at was the scientific evidence from the thermodynamic properties of the universe in light of what's called the Second Law of Thermodynamics. Okay, so it wasn't until the mid-19th century that physicists first discovered and then formulated what we call the three scientific laws of thermodynamics. So the first law of thermodynamics is basically the law of conservation of energy, and it just states, look, energy can neither be created nor destroyed. It can only be transferred or changed from one form to another, right? E equals mc squared type stuff. But the third law of thermodynamics, it states that entropy of a system approaches a constant value as the temperature approaches absolute zero. And then finally, the second law of thermodynamics. This is the only one that we really care about for the most part in this argument. And the second law of thermodynamics, basically, it's a law that states the entropy or disorder of any isolated or closed system always increases it never, so it tends towards what's called thermal equilibrium, which is a heat death. All heat is gone and that sort of thing, and it's at this equilibrium, even temperature all throughout. Basically, the state of maximum disorder for the system. So things tend to break. So in common parlance, things tend to break down. Your car never builds itself up; it always breaks itself down over time. Things tend toward their own ruin or toward their own disorder. And this is the same thing when we're talking about on a cosmic scale. Scientists realize, well, this applies to the universe as well. It's tending to the entropy of the universe as an isolated system. The ultimate isolated system will only ever increase. It will never decrease unless something from an outside system comes in. But given that there's nothing outside the universe on naturalism, well, the scientists and physicists of the 19th century realized, this is a huge, huge problem for us. This proves that the Christian theists are right and the universe must have begun to exist. Because otherwise, on atheistic naturalism, the universe is just a huge closed system with nothing outside of it. There's no God to input energy into the system. So if it was eternal, it should have already broken down. We should be in this maximum state of entropy already. But yet we're not. The universe is in a state of disequilibrium. We're not at that total state of thermal equilibrium yet. And that's, scientifically speaking, how the heck could that be the case? That must prove that the universe began to exist, because otherwise we would be in what scientists call heat death already. Now, one scientist of the time was Ludwig Boltzmann, and he came up with a hypothesis to try and save the eternal universe. So he said, well, look, the greater universe as a whole is in thermal equilibrium, as the scientific Second Law of Thermodynamics proves should be the case. But there are also these random chance fluctuations in this sea of diffuse energy that comes up, and these chance fluctuations result in isolated regions of disequilibrium. And that's what Boltzmann proposed our observable universe might be. It's just an isolated region or an isolated pocket of thermal disequilibrium within the grander cosmos or universe as a whole, which is in fact in a state of heat death, as would be predicted by the Second Law of Thermodynamics over the course of eternity. So that was his suggestion to try to avoid the obvious implications of the thermodynamic properties of the universe, as well are the observable universe, as well as the Second Law of Thermodynamics there. But this was an explanation that popped up in the 19th century, and it was very quickly dismissed on a couple of grounds. So in the first place, if the universe if little isolated pockets of thermal disequilibrium were able to pop up simply through random chance fluctuations within a diffuse sea of energy and that sort of thing in this grander universe as a whole, well then it would be vastly more probable that, a random chance fluctuation would only produce an observable universe the size of our solar system compared to the massive billions of light years across so many galaxies and galaxy clusters and everything like that. It's astronomically improbable that the observable universe, if it were the result of a random fluctuation of energy, would be the size of our universe versus something smaller like our solar system or that sort of thing. And a second powerful objection against this is, likewise, it's immensely more probable if this, Boltzmann is right in his thesis that the universe is just a random fluctuation, that the observable universe just popped into being 5 minutes ago, complete with the appearance of age, rather than having existed over billions of years and sustained its existence over billions of years. Random fluctuations, and the quantum world pop in and out of being all the time and that sort of thing. So it would have popped into being and then popped out of being and that sort of thing. So in the light of this fact, now just a quick note, we will be seeing that there are modern quantum takes on this random fluctuation idea, but just looking at Boltzmann's idea on the face of it, this is why every scientist in the world today rejects what he offered as the solution, and it's become known as the Boltzmann brain problem, which basically says, look, if the Boltzmann's idea is true, well then it's vastly more probable that I'm just a brain that popped into existence 5 minutes ago, complete with fake memories of the universe or my existing for years and that sort of thing. That's all an illusion. And the universe around me, that's all an illusion. I'm just a brain that exists, a thinking brain, and that's the only thing that exists. So, that kind of solipsist view is vastly, astronomically more probable than what we see with our evidence on Boltzmann's proposal. And that's why basically every scientist in the world today rejects Boltzmann's idea, at least as he laid it out back in the 19th century. And believe it or not, this problem has just gotten worse in the 20th century, getting into the accelerated expansion rate of the universe, which we'll find out in the second scientific evidence when we get to that a little bit more detail later on. But that is problematic for this Boltzmann brain notion of these isolated pockets of diffuse energy as well, because the universe is expanding at an accelerated rate. The galaxies and that are getting increasingly further and further away from each other, faster and faster. So in light of this creates problems, because the hypothetical regions or pockets of diffuse energy fluctuations that Boltzmann is pretending our universe is just one of those in this wider universe ensemble, they would just become increasingly more and more isolated over the course of all eternity, if this were true. So these causally disconnected pockets of energy, if it were truly eternal in the past, these fluctuations, then the regions should have long since all have gone cold, dark, dilute, and lifeless. So even if it was true, it's impossible to see the universe today that we're looking at. And based on this, astrophysicist Dr. P.C.W. Davies, or Paul Davies, this is what causes him to exclaim, quote unquote, the universe can't have existed forever. We know there must have been an absolute beginning a finite time ago. So that's quite the quote from Paul Davies in light of the second law of thermodynamics and the accelerated expansion rate in response to Boltzmann's theory here. That said, some atheists and skeptics have tried to deny the obvious implications of the second law of thermodynamics that we have here. They'll postulate something called Brownian Ratchets, or it's a form of perpetual motion machine, and they say, well, these can deny the second law of thermodynamics. Obviously, from that you can extrapolate. Well, if it's possible for there to be violations to the second law of thermodynamics with these Brownian ratchets, well, maybe we can apply that to the universe as a whole with these random fluctuations. It was a closed system, and maybe the universe as a whole was some kind of Brownian ratchet or perpetual motion machine, and that explains why the universe could be eternal in light of the second law of thermodynamics. It was a Brownian ratchet, which is a violation of the second law of thermodynamics. So obviously this all hinges on whether or not it is possible to have these Brownian ratchets or not. And believe it or not, this idea was first analyzed back in the 20th century, 1912, so the same year the Titanic sank. And it was brought up as a thought experiment by the Polish physicist Marian, can't pronounce his last name, Smoluchowski. And it was really popularized later on by the famous Nobel laureate physicist Dr. Richard Feynman. Everyone knows him. But yeah, so essentially the Brownian ratchet, it's a simple machine consisting of a tiny paddle wheel and then a ratchet where it's able to extract useful work from random fluctuations. Remember, harkening back to Boltzmann, in the form of heat within that closed system, if it were to exist in reality, would constitute a violation of the second law of thermodynamics. Look, things are not increasing in their entropy here. Now, Feynman, he rejected this idea, and if you go to my blog site and read the chapter, I've got a video source from back in the 1950s of him giving a lecture of why this thing is scientifically impossible to occur, because he basically demonstrated that, look, that if the entire device is at the same temperature in this maximal state of entropy, then the ratchet will simply not rotate continuously in one direction. It'll actually move randomly back and forth, and therefore it will not produce any useful work throughout time. He had some other objections to this notion as well. You can see that in the blog post on my blog site, in my 200-page chapter on the cosmological argument. I go into the details as well, provide the link to that video of Richard Feynman himself making the case against this in a 1-hour lecture there. But this really sort of made it conclusive that such a notion is impossible, and therefore the second law of thermodynamics is still being upheld. Now, it's important to note that there was a recent experiment done in 2018, based on a scientific experiment by Tongkang Li from Purdue University, as well as some other colleagues that Li worked with. However, the main point here, though, is that the atheists and skeptics, when they use this, are totally wrong. They're out to lunch. And you can confirm this yourself. I've linked to the actual peer-reviewed paper, as well as critiques by scientists and experts. And, this is what I've found. They've actually found that their results are consistent. They don't disprove or violate the second law of thermodynamics. They actually uphold the second law of thermodynamics. They confirm that it's true. So one of the scientists giving his sort of take is physicist Devaraj Vandermeer. He's from the University of Twente. And he basically said this, quote unquote, "The machine produced by Tongkang and company doesn't come close to violating the second law of thermodynamics. Doesn't even come close. Since the system is extremely inefficient, meaning it could not last over eternity or perpetually, it would break down just like everything else, thereby confirming the second law of thermodynamics." And even more telling, Li and the other scientists who did the experiment themselves admit that their results are fully confirmatory of the second law of thermodynamics. So they say this, quote unquote, "We studied the behavior of the ratchet over a range of temperatures and external loads, demonstrating that it rectifies thermal fluctuations to generate work while obeying the thermodynamic laws." That includes the second law of thermodynamics. Originally derived from macroscopic heat engines operating in cycles. When the temperatures of the two heat reservoirs are equal, we find no unidirectional average drift of the particle in agreement with the second law of thermodynamics. So this is in the conclusion of the peer-reviewed paper by the scientists who conducted this experiment, and they're telling you that their results confirm the truth of the second law of thermodynamics. It's not a violation of the second law of thermodynamics. So yeah, don't believe the popular atheists who pretend that this 2018 experiment of a Brownian ratchet machine disproves the second law of thermodynamics. They don't know what they're talking about. The scientists themselves say, no, it actually confirms the truth of the second law of thermodynamics. No scientist today denies the truth of the second law of thermodynamics. It is the most confirmed and firmly established law in science that we have. Virtually every scientist on the planet will think that you're literally insane if you deny that the second law of thermodynamics is true, universally true, and unexceptionally unexceptionlessly true in our universe. It's basically considered a closed, quote unquote, closed science in the 21st century. It's one of the best. Thermodynamics is one of the best understood fields of modern physics, and this is why you're seen as insane if you reject the truth of the second law of thermodynamics. I had a quote. I can't find it here in my notes, but it was something along the lines of, if someone has a scientific law and they observe something that contradicts that law, then the law might need revision. If somebody observes something that apparently contradicts the laws of thermodynamics, then you need to check your observations. Your observations are out of whack. That's how firmly established the second laws of thermodynamics are. They're almost beyond the possibility of they're seen as beyond the possibility of falsification at this point. So, yeah, one last thing on this thermodynamics issue that I should mention, because some people will say, but the second law of thermodynamics, I'm not so insanely skeptical as to deny it, but maybe at the quantum level there it might not apply. We could have a quantum theory of gravity which may avert the implications of the second law of thermodynamics. So some might try to say, well, maybe it's possible in some kind of quantum gravity regime the second law of thermodynamics simply doesn't apply, and that's certainly true for some laws of physics. The quantum realm is different. General relativity, for example, Einstein's theory of general relativity doesn't apply at the quantum scale, and so maybe it's the same with the second law of thermodynamics. A skeptic might try to imply, but unfortunately for these skeptics, it's been mathematically proven as of 2013 by the famous cosmologist Dr. Aaron Wall of the University of California. He's been able to formulate a new singularity theorem which closes the door on this possibility. Dr. Wall has conclusively demonstrated mathematically that given the validity of the generalized second law of thermodynamics in quantum gravity, the universe simply must have begun to exist, and this generalized second law of thermodynamics applies even at the quantum realm. Now, it is important to note here that there is a difference between the ordinary second law of thermodynamics and the generalized second law of thermodynamics. And Aaron's paper here utilizes the generalized theory of second law of thermodynamics, or GSL. Again, they define that, but it basically just applies it to the quantum realm, and it's been demonstrated that, the second law of thermodynamics as we know it applies in a generalized way even at this quantum level. Thereby, from that, he derives his singularity theorem that the universe must have been begun to exist. We'll get into that part in aspect 2, but just wanted you to know that generalized the second law of thermodynamics does apply at the quantum gravity regime. So you can't evade this evidence by claiming, well, quantum gravity will get us out of it. Sorry, no, you still got to deal with these generalized second law of thermodynamics and the thermodynamic properties of the universe. That's pretty much it in terms of the second law of thermodynamics. It's fairly conclusive at face value. It looks like the second law of thermodynamics is established, and it's going to be really powerful evidence to use when we're establishing aspect 2, that the best explanation of the thermodynamic properties of the universe in light of this second law is the universe must have begun to exist. So let's move on to the second scientific evidence or empirical evidence that we have, and establish this, namely the expansion of the universe. The universe is expanding, and from that data we can also extrapolate various mathematical proofs or singularity theorems which are associated with the expansion of the universe and will be relevant to proving the universe must have begun to exist at some point before the before a singularity. Believe it or not, it wasn't until the 1920s that even 1929, really. I mean, up until the 1920s, most scientists had this biased atheistic assumption that the universe was stationary, static, and eternal. No evidence. They just mindlessly assumed it. And if you remember, we covered in part two Albert Einstein's bias in this on this fact, even laughing and denying the mathematical proof that Christian theists provided to him, proving that his own special theory of relativity proved that the universe must have begun to exist. So yeah, it wasn't really until 1917 AD that Albert Einstein, he first applied his gravitational theory, known as the general theory of relativity, to the universe as a whole. And what happened was, unfortunately for Einstein, he realized that his calculations proved, in a mathematical rigorous sense, that the universe did not exist in a steady state, as he and most other scientists kind of biasly were brainwashed into believing was the case. Now, despite this, Albert Einstein employed an ad hoc element. He was desperate to maintain his biased beliefs and worldview, so he slyly introduced a completely non-evidenced fudge factor into his equations. This was known at the time as the cosmological constant, and he plugged these into the equations to counterbalance the gravitational effects of matter, which basically meant that the universe must have begun to exist. And by introducing this fudge factor into his equations, he could maintain the eternal static universe. There is no evidence for this. Every scientist in the world living today, even ones that believe the universe is eternal, agree that Albert Einstein was a liar when he did this, and it was just bias on his part that caused him to do it. Nothing but sheer skeptical bias. But yeah, so let's see how that, even Einstein himself admits this. But following in order, so in terms of discovering the expansion of the universe, so basically in 1919, so 2 years after Einstein published, his GTR and that sort of thing, the earliest empirical evidence confirming Einstein's GTR was obtained when a solar eclipse provided another scientist named Arthur Eddington, along with his expedition, an opportunity to test a prediction that Einstein's theory made, basically showing that light waves were indeed deflected or bent due to the effects of matter being on space, bending space itself. So for those that don't know, that's what Einstein was famous for there. He thought that space itself was kind of like a sheet, and it bends. When you have a massive object like a bowling ball, it leaves an indent in the sheet. So in the same way, planets, they're massive objects or stars or whatever, moons, whatever it is, they leave indents in space itself, and that's what gravity is. If you rolled a little tennis ball next to a bowling ball on a sheet, the sheet would be indented, and then the tennis ball would be go along the lines of that indentation. Basically, this proved empirically, Arthur Eddington proved empirically, that Einstein was right, because light waves are bending around planets because space itself is bent. So the light waves themselves are being bent as they travel through space around these planets. And these, this experiment was subsequently confirmed by other astronomers, Russell A. Hulse, Joseph H. Tyler, who won the Nobel Prize in 1993, and they've solidified this early scientific finding. Einstein's general theory of relativity is very probably true. Everybody admits it. Even young Earth creationists don't deny it. But what's the relevance of this? How do we go from having GTR to saying, okay, well then the universe is expanding, and therefore if it's expanding, it must have been contracting as we travel back in time, and it can only detract to a certain point. Modern scientists have calculated that to be about 13.8 billion years, plus or minus. So beyond that, it is impossible for the universe to have existed. It could not have existed in a contracting state eternally. It seems Albert Einstein's own equations proves mathematically the universe must have begun to exist at some point in the finite past. And the first point of evidence, so it wasn't really necessarily Einstein, but the Friedmann-Lemaitre equations. They basically, a few years after Einstein published GTR, and it was observationally established in these experiments, a Russian mathematician by the name of Alexander Friedmann in 1922, and totally independently, the Belgian Christian astronomer Georges Lemaitre in 1927 independently provided solutions to Einstein's field equations, which predicted, no, the universe is in fact expanding and therefore must have had a beginning. And this Friedmann-Lemaitre model soon became known by what we all know it today as the quote-unquote standard Big Bang model. Now, as I said, the scientists of the day were deeply biased. So unfortunately, back in 1927, the scientific community, including Albert Einstein as a whole, were not even prepared to consider this notion. Even Albert Einstein apparently had a hissy fit when he met personally with Lemaitre at a conference. Lemaitre showed him the mathematical soundness of his model in Brussels, and this is total rubbish and that sort of thing. So this is the first evidence that we have that the universe is expanding, this Friedmann-Lemaitre equation, this mathematical proof that they provided. Now, the second major evidence, this is really what turned everything around. It's empirical data, observational data that proved the Friedmann-Lemaitre model was true. It was the redshift of the distant starlight. And once this was discovered in 1929, everyone, including Einstein, said, we were wrong. My goodness, the Big Bang is true, or very, very probably true. So this just shattered and changed the entire landscape of cosmology in the 20th century. And what happened was in 1929, the famous astronomer, many people say he's the most famous astronomer of all time, Edwin Hubble, whom the Hubble telescope is named after, he discovered concrete empirical proof that the universe was in fact expanding in the same way as the Friedmann-Lemaitre model or equations had predicted. After about a year of measuring the light coming from, taking detailed scientific measurements from the light coming to us from distant galaxies, of which Hubble was the one to discover that there are in fact other galaxies out there previous to this study. But he noticed that they appeared to be redder than expected. The light was quote-unquote red shifted, as it were. And this Doppler-like effect was known about since the 1840s. It was known that light, just as all waves, were affected by a Doppler-like effect. So for example, with sound waves, as an object moves towards us at speed, the sound waves become compressed, and therefore they get louder. And then as it moves away from us, the sound waves stretch out. They get shifted out, and the sound becomes fainter to us. Well, it's the same deal with light waves as well. As objects move closer toward us, toward the Earth, the light becomes compressed, and that means they get shifted into a higher frequency, or the blue end of the electromagnetic spectrum. They get blue shifted. But as objects move away from us, the light waves stretch out, and they get shifted into the red end of the electromagnetic spectrum. Hence the term, they're red shifted. They look redder, and increasingly redder and redder to us. And that's what this empirical evidence of the redshift from distant galaxies refers to. And Hubble was startled to find this because, wherever he trained his telescope in the night sky, he observed this same redshifting of the light from distant galaxies. And, what's more, he even found that the redshift was roughly proportional to the distances of the stars relative to the planet Earth. Obviously, the Earth is our observation home, our observation point. And this relationship became known as Hubble's Law. So it was this discovery by Edwin Hubble that almost overnight immediately every scientist in the world recognized the most plausible explanation for this empirical data is that, yeah, galaxies must be moving away from us. The universe itself is expanding and stretching the light of these distant galaxies. And consequently, if the universe itself is in fact expanding, well, then that must mean that the static eternal model of the universe cannot be true. It's impossible to be the case. It only makes sense if the universe is expanding. And obviously, if it's expanding, well, through backward extrapolation, this would mean that the universe increasingly gets hotter, denser, and smaller as we travel back in time, and it contracts. And obviously, this implies there must have been a finite beginning point for the universe, because once it reaches what Friedman and Lamont called this singularity point, infinite density, infinite hotness, and all that stuff, well, that's scientifically impossible to reach. Remember, in parts 1, we said actual infinities are impossible anyways. But yeah, you can't get beyond this singularity point. You can't even get to the singularity point, given that actual infinites are impossible. So this means there is a boundary to the universe, and it must have begun to exist. So this is the incredible evidence from the redshift here. Now, it's important to note that there have been, in the past, deniers of this redshift evidence. And believe it or not, it doesn't come from atheists and skeptics, but it actually comes from Christians. Christians have been the most vocal advocates against this incredible redshift evidence proving that the universe began to exist. And believe it or not, it comes in the form of young Earth creationists, or technically speaking, young universe creationists. Because there are some young Earth creationists who believe that the universe is old. For example, Dr. Tony Costa, one of my mentors, who I'm lucky enough to have worked with, and he baptized me and that sort of thing, even he said, well, I believe the Earth is young, possibly our solar system is young, but the universe is old. So it is possible to accept an old universe and still be a young Earth creationist. But there are a lot of young universe creationists back in the 90s and early 2000s, and who were critics of this redshift data or evidence. And they basically said, well, this doesn't prove that the universe is expanding, at least not in terms of space itself. So this is an important aspect. It's with the data, it's the universe itself. Space itself is expanding. It's not that there's space and then the stars and the galaxies are expanding within a static space. Space itself the galaxies are stationary, but space is expanding. Just like if you have a bunch of buttons taped to a balloon represents space, whereas the galaxies are stationary with respect to the balloon as you blow it up. The balloon is what's expanding, space, not the stars within them. So that's what is accounting for this redshift data. And young Earth creationists will say, no, I think that the galaxies are expanding. So that would be the model where the space itself is static, empty space, and the galaxies are expanding within space. So the galaxies are moving away from each other, and that's what's producing this redshift data. There are other options that produce, there are other things that produce a redshift effect in terms of light that they'll appeal to. So one of the options that young Earth creationists or young universe creationists like to go to, for example, Dr. Jason Lisle, an astrophysicist that answers in Genesis, he's also argued that time dilation, relativistic time dilation, can also create a similar redshift effect. Now, obviously, that answer goes with the B theory of time. It's inconsistent with someone who believes in A theory of time. So that can't be true. That can't be the option for us. But again, this argument is time theory independent. So we don't care whether the B theory or A theory is true. So we do have to consider this option. A couple of other now refuted. Like I said, nobody believes these today, but There's been the tired light model, which tried to explain that as the light propagates through space, it loses energy, and then this loss increases its wavelength. That was used to try and explain the redshift data. There's the varying mass model, for example, saying that atomic masses increase as the universe ages, and therefore light from more distant objects was basically emitted when the universe was younger and the masses of the atoms were smaller, and that sort of thing. So, both of these models were developed solely to explain the redshift distance relationship without appealing to continuous cosmic expansion. But these ones have all been refuted. The only live options that young universe creationists went for were, objects within space moving there, or Jason Lyle's time dilation, relativistic time dilation explanation in the early 2000s. So yeah, those are some other ways that claim to be equally probable explanations of the same redshift data. And on top of this, they also point out to various problems. I link to Walt Brown, who mentions the quantization anomalies in the redshift data. So basically, they say, well, there's certain anomalies in the redshift data that we see. They come in discrete, for lack of a better word, discrete entities. They're discrete readings. They're not one continuous value, or sorry, they don't provide continuous values without these discrete values popping up in the readings, and that's weird. Other issues that they'll raise is that now with these things, as I said, these other models have been falsified since, and as we'll see, even the young universe creationists themselves have changed their minds about these other models. So we've gotten data that's refuted it and that sort of thing. But, we do have answers. So with this quantization redshift anomalies, actually we've proven subsequently through statistical calculations that these anomalies are perfectly consistent with continuous spatial expansion. So, these minor anomalies that young universe creationists would point to in the 90s and the early 2000s really do have, readily available explanations to explain it. And I give a link in my write-up on my blog site from Dr. Hawkins and Maddox and Merrifield, who kind of discuss that. Secondly, young universers have also presented problematic data from quasars, the redshift of quasars. And this has been used to raise doubts that the cosmic expansion interpretation is true. But modern work scientific investigations have proven that this is false. It actually does prove that the cosmic expansion thesis is true. So here's a quote from a paper that I linked to on my blog site in my chapter. Quote unquote, the relation between the absorption and emission redshifts predicted by current cosmological models is well obeyed. The result confirms that redshifts of quasars are indeed distance indicators, and it might be the most obvious evidence found so far to be consistent with the cosmological interpretation of quasar redshifts. So contrary to the claims of young universers back in the 90s and early 2000s, all of the data has been confirmed to precisely fit a cosmic expansion thesis. But it goes even further than this, because when we were checking out the redshift data from these anomalous quasars and that sort of thing that were considered problems, and we discovered that actually it's not a problem. Given our statistical assessments and modern evidence, we've proved that it's actually exactly what would be expected if space itself were expanding. But not only that, when we were trying to defend ourselves against this young universe attack, we actually got positive evidence that proved from the redshifts data of these quasars that only the spatial expansion of the universe model explains what the redshift data that we get from these quasars. All the other young universe cosmological models are falsified by it. And essentially what it is they found in terms of distant quasars, there are usually gas clouds and stuff like that in between the planet Earth and those distant quasars. And these gas clouds will actually absorb some of the light. So these come across in the redshift data as dark absorption lines within the spectra from these distant quasars. Because obviously the gas clouds, and there are multiple gas clouds in some cases at different distances from us. We not only got one of these dark absorption lines, we got several different ones, all corresponding to where these gas clouds were at varying distances between us and these quasars. And that gave us the redshift values came out as exactly as predicted on the cosmological expansion interpretation. And it falsified what we would expect from other models. Makes sense on the cosmic expansion model. And, we got this, what's called a forest, a Lyman alpha forest in terms of the redshift data. So this was powerful confirmation that the redshift data does support the cosmic expansion thesis. Now, as though this wasn't enough, we also have another line of scientific evidence based on redshift data that is also scientifically falsified, almost with absolute certainty, all other explanations or models for the redshift data that we have apart from the standard Big Bang model, the cosmic expansion, space itself is expanding. And as I said, this was done with near absolute certainty. So I'm going to quote astronomer Dr. Hugh Ross here from Reasons to Believe. And word for word, reading everything, he says, quote unquote, "The most widely accepted young universe model acknowledges that while the universe exhibits billions of years of development, due to a hypothesized gravitational time dilation effect, only a few thousand years have elapsed on Earth. In other words, the rates of all distant phenomena occur thousands to millions of times faster when measured from Earth. Standard Big Bang models or cosmic expansion models, on the other hand, predict the opposite, that velocity time dilation effects will make very distant phenomena appear to proceed more slowly, by a few tens of percent, something like that. Now, recently, a team of American astronomers developed and applied a robust new method for testing and distinguishing among the different models. What this test does, it involves multiple spectral measurements of type 1a supernova eruption events. They last about 7 months in the absence of time dilation effects. And then the team looked at, well, how do the different spectral line intensities change over the supernova eruption phase, and thus determine how far into the 7-month period the eruption has progressed. So the time dilation factor is determined by dividing the time between observations by the change in time progressed into the eruption. So that's the calculation they do. So an astronomer made 2 spectral observations 20 days apart, and then determined the time progressed into the eruption was 10 days and 26 days respectively. So in this case, the time dilation factor would be 20 divided by 26 minus 10, which gives us a factor of 1.25. Based on this redshift data, you don't have to understand the math or that sort of thing. I'm just reading the quote. But so we got this time dilation factor of 1.25 from studying the redshift spectral data from these supernova that last for about 7 months. Now, for a static or semi-static universe model, the time dilation factor would be 1. For a young universe, the time dilation factor should be near 0. And then finally, for a Big Bang universe, the time dilation factor should be 1 plus the redshift value of the whatever object you're looking at, galaxy or quasar or whatever it is. So in this case, the objects are those supernova, those stars. So basically what they found so far is that the method has been accurately applied to one distant supernova, 1997 EX, and the results were perfectly consistent with the continuous cosmic expansion from a cosmic creation event about 14 billion years ago. Precisely matched up what it was supposed to be on that model, and this thereby falsifies Jason Lyle's or the Young universe models and that sort of thing. So they definitively falsified both the non-expanding universe models and the Young universe models single-handedly with this single discovery and observation. So yeah, this was incredible evidence based on redshift data that proves space itself is expanding, just as the standard Big Bang model predicts. Now, believe it or not, we've got another final line of evidence, and that's the fact that the Young universe scientists themselves are now admitting, yep, cosmic expansion is true based on the redshift data. So, yeah, I had a quote here in my book from famous Young universe creationists who back in the early 2000s denied that the redshift proved that space itself was expanding. He's now written an article totally the opposite. So Dr. Danny Faulkner from Answers in Genesis is who I'm talking here. And he's written an article which I linked to called The Case for Cosmological Redshifts, in which he admits, yeah, I'm sorry if you guys don't like this, but it's basically confirmed that space itself is expanding and is proved through this redshift data that we have up to date. So, just to quote a little quote from him here. So, since recent creationists reject the Big Bang model and a timescale of billions of years, how do we properly interpret quasars, i.e. the redshift data from these quasars, and the issues that they raise? The answer to that question is not obvious. The answer likely will be related to how one answers the light travel problem. If recent creationists continue to argue against cosmological redshifts and their implication for a spatial expansion, then it is unlikely that they can develop a correct cosmology. Also within the same paper, Danny Faulkner also mentions this, quote unquote, recent creationists often use the possibility that redshifts may be quantized as evidence that we are at the center of the universe. And this is usually flat earthers say this too. They still believe this. They're kind of behind the times. But it's based on scholars or scientists like Dr. Russ Humphreys and his 2002 research, white hole cosmology and that sort of thing, which we'll address a little bit later on in aspect 2. But basically, yeah, before Russ Humphreys himself denied the redshifts data, proved that space is expanding and that sort of thing. Incidentally, though, Humphreys has also, like Danny Faulkner, has now done a 180-degree turn, and he's opined in an article that he wrote that after spending many years opposing universal cosmological expansion of space itself as the cause of the redshift data, he has now come to accept some form of spatial expansion as the cause of this redshift data. It is undeniable. Yeah, it's just one last quote. Again, these are from young Earth creationists who used to just about 15 years ago were denying that spatial expansion was taking place. And they say, quote unquote, look, many recent creationists appear to oppose the Hubble relation, the expansion of the universe, and cosmological redshifts of quasars. Here, I examine these 3 topics. There are good reasons for accepting all 3 of these theses. The rejection of these topics by many young Earth creationists appears to be only motivated by fear of possible evolutionary implications. So he's meaning to say, look, even if you accept there's spatial extension of the universe, that doesn't necessarily mean that the Big Bang theory is true. And the Big Bang theory, billions of years, is what they're against. So you can have spatial expansion, but that doesn't necessarily carry with it these evolutionary implications. And I'll cover that again when we get to aspect number 2. Continuing the quote, it is not clear what motivates this false thinking. Some of these writers apparently do not understand that rejection of cosmic expansion is tantamount to a rejection of general relativity, and rejection of cosmological redshifts could therefore stifle development of any true hope for a true biblical cosmology. So yeah, that's the principle of enemy attestation right there. The young universers themselves are now coming to the table and saying the subsequent evidence just makes it impossible to maintain that. Yes, space itself is expanding, and it's been proven by this redshift data, and they accept it now. They're starting, the astrophysicists that work at Answers in Genesis and that sort of thing, and Russ Humphreys, one of the most famous young Earth creationist scientists in the field of cosmology that they have, he's reluctantly admitted the truth that space is expanding based on this redshift data as well. So yeah, that's some incredible testimony right there, and evidence from enemy attestation. So yeah, okay, with that said, moving on, that's it for the redshift data. Okay, but we're not done. We've got even more evidence that the universe is in fact expanding. And this is, again, empirical evidence dating back to the early 20th century. And it comes about in the year 1930, but it's the abundance of light elements, or specifically helium atoms, in the universe. So the astronomer Cecilia Helena Payne, Gopushkin, basically, she surveyed all the stars in the Milky Way galaxy that were brighter than the 10th magnitude. And she also studied some variable stars, over 1 million, 1,250,000, I think, something like that. And as well, 2 million stars from the Magellanic clouds. And using her spectral instruments, she found out that more than 98% of the matter in the entire universe is either hydrogen or helium. And there are trace elements of other light elements. And this fits the standard Big Bang model. It's hotter, it's denser, therefore the hotter and denser the universe was back in time, that means that heavier elements can't form, it requires more space and less heat and that sort of thing. So only, in the early universe, it looks like only hydrogen and helium and small amounts of other light elements were able to form. And that's why we have this abundance of it throughout the entire universe, but the heavier elements we don't have. And just to break that up, so more than 98% of the matter is either hydrogen or helium in the universe. About 24 to 25% of the visible atoms in the universe are helium. These things, there's too much helium in the universe to have been formed in stars through stellar nucleosynthesis or supernova action. So there shouldn't be this much helium in the universe. So that just means that, well, the only alternative situation to have is that at some, quote unquote, at some point in the past, the entire universe was under a lot of pressure, close together, and generating a lot of heat. During this earlier phase of the universe, it was too energetic for even protons and neutrons to form. But after it cooled enough for them to form, and while they were still at piping hot temperatures and relatively densely packed, they must have smashed into each other and produced helium. So this phenomenon was nicknamed Big Bang nucleosynthesis. And this is the next empirical evidence that they found that proves, yeah, the universe, if you extrapolate back in time, was much hotter, much denser, and that thereby proves that the universe is expanding through time. It's been growing bigger, less hot, less dense. Now, believe it or not, the young universe creationists don't really even deny the scientific facts in this case. Again, all the atheists, they all admit this evidence. It's really only the young universe creationists who would have a problem with this kind of thing. And what they do is they object to the implications of this finding rather than the evidence itself. So, they'll come up with objections. So, for example, they'll say, well, in the first place, even though this is true, this abundance of helium and hydrogen in the universe, that doesn't prove that the Big Bang model is true. Your predictions or your model is made after the fact, just to fit the facts. So that's a major objection that young universe creationists give. They will also object that the Big Bang model is able to be adjusted indefinitely as the need arises in order to fit any subsequent observations, because the helium to hydrogen ratio is entirely dependent upon what's called the baryon number. The baryon number just refers to the ratio of baryons to photons. And yeah, that can be adjusted to accommodate the needs of any problematic data and make it reconcile with the Big Bang theory. They also appeal to various mysteries. So, for example, they'll say, well, if what the Big Bang theory is true and accounts for this hydrogen and helium, being formed all at once in this very hot, dense, early phase of the universe, well, then how come we lack a sufficient amount of antimatter to make the Big Bang theory true? Yeah, so with that, they're sort of rejecting the notion that the helium and hydrogen abundance has anything to do with the universe expanding from a once very hot, very dense stage. Yeah, and there are some other objections as well. So one thing, they'll appeal to missing helium hydride, which was something that scientists haven't been, the Big Bang theory predicts this. If this light element abundance is responsible from the Big Bang, consistent with cosmic expansion from this early hot dense stage of Big Bang nucleosynthesis, whereas we should expect to find helium hydride, and they'll say, well, we don't see it. We've looked for it and we can't find it. So these are some of the objections that young universe creationists will give against this scientific evidence proving that cosmic expansion is in fact taking place from a very hot, dense, and pressurized state. By way of retort, so in the first place, in terms of the first couple of objections, it can be, it's just after the fact. We made the theory to fit the facts as we observed it. Well, this isn't true, because the Big Bang theory model makes specific predictions that have been subsequently confirmed after the development of the theory and that sort of things. And that, the Big Bang model, in terms of it just being made to fit the facts as it existed in the late 1920s or 1930s. So obviously that's not true, because it's made further predictions, and those have subsequently been confirmed through scientific observations. That said, even if it was true, let's pretend for the moment that it was true, they saw the facts and they concocted this theory after the fact, that still doesn't matter. It still is an explanation of the data that we have, and we do have to reconcile this data and explain it. And this provides a perfectly plausible explanation for it, whereas young universers don't have anything really that can adequately explain the data we have in terms of the current ratios of hydrogen and helium and that sort of thing. Now, going hand in hand with the notion that, you can just make an infinite number of modifications to the theory to fit any subsequent observations that are inconsistent with the Big Bang theory and the notion of Big Bang nucleosynthesis. Once again, basically, cosmologists make very precise predictions about the relative abundance of the light elements from BBN. And, the primordial element abundance depends on several parameters. And that makes it hard to just fudge around with it whenever you want to. That kind of objection, this objection that it's all just a big dishonest scam, that doesn't hold water. Now, responding to the more substantive objections, one of the major pieces of evidence for the Big Bang theory is that we do have these consistent observations that as we look at older and older objects, we observe that the abundance of heavier elements becomes increasingly smaller and smaller, basically asymptoting to zero. By contrast, the abundance of helium goes to a non-zero limiting value. Wherever you look, doesn't matter how old the objects are, the amount of helium is still 24 to 25% of the total mass of normal matter. Now that corresponds perfectly with the cosmic expansion thesis from this early phase where it was very hot, very dense, and only hydrogen and helium could form. Only these two light elements could form and that sort of thing. So that does not fit an eternal steady state model or any of the young universe creationist cosmological models. That fits this cosmic expansion theory perfectly. Yeah, why is it that the amount of helium stays the same no matter how old the object is that you're looking at, but the other elements, well, it depends how old it is as to whether we find, what the abundance of the heavier elements turn out to be. Now, the other objection they mentioned, so there's this matter-antimatter asymmetry problem that young universe creationists will give against the using the light element abundance as proof of the Big Bang theory. And essentially, modern solutions to this problem depend on the so-called electroweak symmetry breaking. So what that is, so at sufficiently high temperatures, the electromagnetic force and the weak force are essentially indistinguishable. They unite into a single force, as it were. So essentially what happened as the universe was cooling below a temperature of about 10 to the power of 15 degrees Kelvin, these forces then separated because it cooled to the point where they could separate into distinct forces just as we see them today. And it was this phase transition that led to the required thermal non-equilibrium. So the violation of the CP symmetry is naturally built into the electroweak theory. So yeah, they do have an explanation for this. So just to give you sort of a quote on this specific issue from actual scientists, again, sources in my blog, quote unquote, most particle physicists and cosmologists today are absolutely confident that this kind of solution is the right track and that the problem of the matter-antimatter asymmetry will be solved completely satisfactorily. And finally, in terms of the problem of the missing helium hydride, so I quote Dr. Hugh Ross, astronomer Dr. Hugh Ross from Reasons to Believe, and he sort of says, look, yes, this is true. The young universe creationists were correct to ask, where is the helium hydride? Because astronomers, for decades, they were searching for this helium hydride, as was predicted, but they always turned up empty. And then, quoting Dr. Hugh Ross, until now, quote unquote, until now, one planetary nebula is very young, it's about 600 years old, and especially dense. The planetary nebula NGC 7027 is also one of the visually brightest planetary nebulae. Rolf Gustin and his team of 9 other astronomers discovered scientifically the presence of helium hydride, exactly of the biblically predicted Big Bang creation model has been affirmed. So they've finally discovered it. So this has been answered. We've discovered that the missing helium hydride is no longer missing. Therefore, all of the objections that young universe creationists give against this evidence from the abundance of helium and hydrogen in the universe, being consistent everywhere in the universe, staying exactly the same wherever you look, no matter how old the objects are and that sort of thing, or how far away the objects are, has been confirmed. And there are no plausible objections that haven't been refuted or aren't plausibly refuted. So yeah, I think this is some proof that we've been having cosmic expansion, and that this cosmic expansion can be traced back to a very early moment in the early universe's history, a very hot, very dense, very pressurized state. Okay, so the next major piece of evidence, and this is probably the most important empirical evidence that proves cosmic expansion of the universe is true, and that prima facie the Big Bang theory is the true explanation for it and that sort of thing, is the CMB radiation, otherwise known as the cosmic microwave background radiation. And basically, this was discovered in 1965 by accident by a couple of employees at Bell, Arnio Penzias and Robert Wilson. And they discovered this by accident, this CMB radiation. So what this is, so essentially under the Big Bang theory, the notion is, hey, the universe space itself is expanding from this initially very hot, dense state. Okay, on this prediction, that would mean that the universe would have gas within it, and this gas would be cooling as the universe expanded, increasingly getting colder and colder and stretching out and that sort of thing. So, obviously the gas, as you extrapolate back in time, the gas in the universe would have been much denser and much hotter. If the universe did start out from this very hot, dense state, then we would expect everywhere in the universe it should be filled with leftover remnants of the radiation that permeated the earlier phase of the universe isotropic. And yeah, this was, as I said, it was discovered in 1965 by Arnio Penzias and Robert Wilson, and it was confirmed. Um, Subsequent experiments, with WMAP, basically are experiments to find the CMB, and these all confirm the existence of it. At first, it was proven to be isotropic, so uniform. This radiation was uniform everywhere in the universe within 1 part of 1,000. But subsequent experiments have shown that it's actually even more uniform or isotropic than that. It's a uniform temperature, or heat or that sort of thing, within 1 part of 100,000. And where this comes from, this comes from about 300,000 to 400,000 years after the Big Bang model started. So it's a little bit later than when the light abundant elements of helium and hydrogen would have formed. It's considerably later than that, but it's still a very early phase of the universe that the radiation comes from. Now, it's important, as the universe expanded, this radiation was stretched, just like with the redshift and that sort of thing. But in this case, because it's been expanded to such a degree, scientists say by a factor of about 1,000, so that it's actually now in the microwave portion of the electromagnetic spectrum. So this CMB radiation was a major prediction. It basically led the vast majority of scientists to say, yep, the universe is expanding, and the majority of scientists, because of this evidence, single-handedly today, go, yes, the Big Bang Theory is the best explanation that we have. And as we'll see, even skeptics will admit that much. So it confirmed, yes, there is this CMB radiation. It is remarkably uniform. It has the same temperature everywhere within it, within 1 part in 100,000. And secondly, it also confirmed that the CMB is basically, it has a black body spectrum. Okay, so great. Who would object to this? Well, as we've been seeing, atheists and skeptics love it. They fully go, yep, you're absolutely right. So it's once again the young universe creationists, the people who are against the Big Bang Theory and that sort of thing, who would really take issue with this evidence. And some of the biggest objections to this from young universe creationists, again, these are Christians that don't like the secular evidence here, and they'll point to things like the flatness problem or the horizon problem. These are major objections to the standard Big Bang model that people have put forward, and they emerge from the CMB measurements that we've gotten. However, in today's cosmology in the 21st century, those issues have really largely been resolved in modern cosmology, mostly through the use of some kind of notion of a cosmic inflationary mechanism, which we'll learn about. So the standard, we'll learn about that more in aspect 2, but there's a coping mechanism through cosmic inflation will help take care of a lot of the problems that young universe creationists like to raise on this front, including the flatness problem, horizon problem, those sorts of common objections that you'll hear. But really the biggest problem, the one that all the other objections are really ultimately derived from, is really the fact that, look, the CMB radiation, it's remarkably uniform, 1 part in 100,000, but it's not perfectly uniform. It's not entirely uniform. And just to quote Dr. Max Tegmark, a secular scientist here, so, quote unquote, we had expected that the microwave background radiation would be truly isotropic, homogeneous or uniform entirely, 100%, with no preferred direction in space. But the CMB is not perfectly isotropic. And whoops, okay, well, how do we make sense of this? It should be fully isotropic, shouldn't it? If it's all uniform from this early phase, now it's been expanding with space itself. These CMB anisotropies meaning not isotropic, it's not uniform. Well, believe it or not, these CMB anisotropies are not as problematic for Big Bang theorists as young universe creationists would like you to believe. In fact, these CMB radiation fluctuations fit precisely specific scientific predictions made based on the very latest scientific experiments. So it's actually, we would expect these very minor, extremely minor anisotropies to take place if the Big Bang theory were true. And scientists have, explained this and said, well, look, the seeds of these inhomogeneities or these anisotropies were really laid down during cosmic inflation period. And just I keep using this, so just very quickly here and now in aspect one, I'll just explain. So cosmic inflation is just right in the earliest stages of the universe's formation. There was a phase of super rapid expansion up to a certain point, and then it stopped, and we go into our ordinary accelerating expansion that we have today. So yeah, the main point here is, look, regardless of whether you want to accept the Big Bang model or not, Big Bang theory, or billions of years or not, the CMB radiation proves that the universe is cosmically expanding, meaning space itself is expanding and has been expanding from a very early, hot, dense, and pressurized state. That much is scientifically proven beyond reasonable doubt. As I said, even the young universe creationists are coming around and saying, yes, the CMB data, as well as the redshift data, confirms it. So yeah, it's unreasonable if you deny that the universe is expanding just based on these empirical evidences thus far. Now, just before we move on to aspect two, there are two more empirical, or rather mathematical, evidences that I want to provide here in the form of singularity theorems. So these are mathematical theorems that are associated with the evidence from the expansion rate of the universe. The accelerating, again, that expansion rate is actually accelerating over time, just to clarify, so it's an accelerated expansion rate. But these theorems are associated. They say, okay, great, we've got proof for the expansion rate of the universe. These prove that it must have begun to exist at or before a point of singularity. So that's what singularity theorems do. So the first one to get familiar with here came out in 1970 with the Hawking-Penrose singularity theorem. And what this was, it was basically a mathematical proof that proved, given that the universe has been proven to be expanding and is governed, so long as it's governed by the equations of Einstein's general theory of relativity, which we've already seen has been proven beyond reasonable doubt to be true, then given that, the universe must shrink down to an initial singularity, meaning the universe must have begun to exist a finite time ago. Case closed, it's mathematically proven, game over atheists and skeptics. Now, with this was the Hawking-Penrose singularity theorem gave us a major advantage over the previous Friedman and Lemaitre equations that we mentioned as our first piece of data here, our first empirical evidence or mathematical evidence. Those equations basically weren't sufficient to rule out the possibility of small deviations from general relativity, and therefore, just based on those equations, you could possibly avoid the beginning of the universe. Because basically we found out our universe is not completely homogeneous or isotropic at all scales, right? There are those anisotropies that we mentioned with the CMB data, the cosmic microwave background radiation. And this meant that it was still possible that a slight anisotropy might result in the universe sort of slingshotting past itself, and you can get various models like the eternal oscillating cosmological model that will address in aspect 2 in further detail below. But the point here, the importance for the Hawking-Penrose singularity theorem is that they got rid of that. They disproved absolute proof that those cannot be real, because regardless of any anisotropies in the universe, so long as GTR is true and the universe is expanding, then it's absolutely proven that it must have begun from a finite singularity point, a point of infinite density, infinite things, or that. So that proves that the universe must have begun to exist. As physicist Dr. Wald says, quote unquote, our universe simply must be singular, given the Hawking-Penrose singularity theorem. Now, that said, okay, doesn't that mean it's game over? Why are atheists and skeptics still going around and pretending that there can be eternal cosmological models? including Hawking and Doctors Hawking and Penrose themselves. They violate their own mathematical proof. And the reason for this is because their singularity theorem is based on the assumption that 5 conditions are met. If any one of those 5 conditions are not assumed or not met, then this means you can avoid the implications of the singularity theorem and avoid an absolute beginning of the universe. So those 5 conditions are basically going to form the foundation of what we do in aspect 2 when we're studying most of the cosmological models. That's sort of the framework where all modern eternal cosmological models that atheists provide basically appeal to denying one of these 5 conditions. So what are these 5 conditions? So the first one is the Hawking-Penrose singularity theorems apply only if, 1, there's satisfaction of the strong energy condition. So this is typically relating to normal, quote-unquote normal types of matter. So if you posit a violation of this condition, well, that usually translates into what we're going to find out are eternal inflation models. And there are various types of models that fit under that category. The second condition is that there has to be the satisfaction of the generic energy condition. So this means we don't allow for any exotic, what are called exotic or non-normal properties of space and time that might prevent gravitational focusing. So basically, if you posit a violation of this condition, well, that would translate into an eternal exotic space-time model. Number 3, the third condition is that there can't be any closed time loops. So basically, you have to say that the future, on the B theory of time, you can't say that the future does not bend back to become its own past. So obviously, if you violate this condition, well, then that translates directly into a closed time loop or closed time curve model, a CTC model, where the universe could be eternal in the past, as sort of an eternal time machine, so to speak. The fourth condition is that there is a point that past directed world lines emanating from that point have negative expansion. So in other words, they are focused back on each other, and the world lines of observers don't trace into an infinite past given sufficiently concentrated matter, but are focused as by a lens. So what the heck does that mean? This is one I don't understand, but essentially a violation of this condition translates into models with no closed trapped surface of the universe in our past. So you can get an eternal universe this way and avoid Hawking-Penrose's singularity theorem or proof. And finally, the fifth condition, as we saw, is that, well, the general theory of relativity must govern the universe. I mentioned this right at the beginning. Violation of this condition means that, GTR doesn't apply. And as we'll see, this will translate into various eternal quantum gravity models, because if you remember, at the quantum scale, GTR breaks down. It doesn't apply to objects that are that small at the quantum level. And if the universe has been expanding for all eternity, at some point, it would have if we travel back in time, it's contracting. And at some point, it would have been so small, it would have been on the quantum level where GTR simply doesn't apply. So if you posit violations to this, then this usually translates to eternal quantum gravity cosmological models. So that's how we understand there. So right away, it's important to mention that only 3 of these conditions provide the framework or a plausible or reasonable basis for an eternal cosmological model. So 2 of these conditions can just be eliminated as being proven fulfilled beyond all reasonable doubt. And this is a quote directly from Dr. Stephen Hawking, who says this, because he says, quote unquote, we would absolutely expect beyond all reasonable doubt our past to feature a closed, trapped surface, and there is no reason to postulate an exotic space-time construction that just so happens to have perfect defocusing characteristics so as to counter the effects of gravity. So right away, everyone agrees, no one in the world denies this, so you don't have to worry about atheists and skeptics, but right away we can say it's proven beyond reasonable doubt that conditions 2 and 4 are in fact satisfied. So, as I said, yeah, as we get to aspect 2 and start evaluating the various cosmological models, bear in mind that there are only 3 exceptions or violations where it's reasonable to posit that those conditions don't apply, and therefore you can escape the Hawking-Penrose singularity theorem. Okay, so the last empirical evidence, again, it's the exact same type of the Hawking-Penrose. This is a mathematical singularity theorem that proves, given certain assumptions, that the universe must have begun at a singularity point in the finite past. And this is the famous Borde-Vilenkin-Guth, or BVG, singularity theorem, which was demonstrated to be true in 2003, so very recent. And this revolutionized the field by doctors Arvin Borde, Alan Guth, and Alexander Vilenkin. Basically, this theorem provided quote-unquote absolute proof that any universe that is quote-unquote on average in a state of cosmic expansion over its history cannot be infinite in the past, but must have a beginning. Therefore, Hawking's notion that Hawking made certain assumptions, this bypasses that. Even if those assumptions, assuming GTR must be true, you don't even need to do that. As long as the universe is on average, that word is important, as we'll see later on average, is in a state of cosmic expansion. Again, we've observed the universe is definitely been in a state of cosmic expansion. So the trick will be, well, has it been in a state of cosmic expansion on average? We'll get to that later in aspect 2. But yeah, as long as we have that, it's absolutely proven, 100%, the universe must have had a beginning, and therefore it's a contingent thing. It's not eternal. As I said, it also bypasses any need to make assumptions about the material content of the universe. So it holds independently of any and all physical descriptions of the early universe. It applies whether you apply this to an expanding physical multiverse. If you believe in the multiverse, doesn't matter whether there's one universe or an entire multiverse, a multiverse ensemble or something like that. Totally irrelevant. And like I said, yeah, it works whether gravity is described by GTR, general relativity equations, or not. Who cares? Now, what's more, following up on this, in 2012, Alexander Vilenkin showed that even universes or multiverse models that don't meet the general condition of postulating a state of cosmic expansion over its history, on average, nevertheless, even those cannot be infinite in the past, but those must have beginnings as well, because they fail for other reasons to avert the beginning. So just to quote Vilenkin here, quote unquote, look, he says about this, in 2012, he says, quote unquote, none of these scenarios can actually be past eternal. All the evidence we have says that the universe had a beginning. It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. You have to face the problem of a cosmic beginning. Wow, if you're an atheist or a skeptic, I would be very scared right now. If you want to deny this premise, you're in absolute trouble. The experts are saying, we have proof in the place, you're an unreasonable man if you dare say that the universe was eternal. That said, just a note, so the 2012 proof from Alexander Vilenkin is a mathematical proof, it's been established and that sort of thing. Nonetheless, just for safety's sake, because the 2003 version of the BVG singularity theorem is universally accepted by everyone and it's been firmly established, I'm just going to go on the basis of the 2003 BVG singularity theorem. I'm not even going to use the 2012 Alexander Vilenkin modification that proved you don't even need cosmic expansion on average. That doesn't even matter to get this beginning. Just because that one is the universally accepted one without any controversy and that sort of thing. But I just wanted to make you guys aware that there was this further proof from Vilenkin in 2012 that doesn't even require that general condition of the cosmic expansion on average over its history, and still proves mathematically that there's a beginning. So that's interesting here. So yeah, as I said, the BVG singularity theorem from 2003 at least is almost universally accepted by all cosmologists today. At one time, there was a notable exception, though. Dr. Andre Linde, who's a famous physicist, he once suggested that the singularity theorem might not apply in a specific case. He basically said, well, maybe it only applies to the individual parts of the universe, but not the universe as a whole. But yeah, that's been totally rejected and refuted. Even Andre Linde himself said, yep, that was quite wrong and foolish. There are no regional singularities. There is only the universal singularity based on the BVG theorem. So yeah, even Linde himself has now abandoned that objection. Now, it is important to note, so there are, again, with this BVG theorem, it works under certain conditions. So there are about 4, possibly 5 exception conditions to this BVG singularity theorem, and it's on the basis of these exceptions that, as we'll see in aspect 2, skeptics and atheists now base their eternal cosmological models on, and they're going to be on the basis of these exceptions. So basically, what are these conditions for the BVG singularity theorem to be upheld and prove that the universe began to exist? Number 1, you have to fulfill the condition of infinite contraction. So you can't no de Sitter cosmology, what's called de Sitter cosmology. You have to avoid asymptotically static models. You have to avoid infinite cyclicity models. And then finally 4, you have to avoid any time reversals that might have happened at the singularity moment. And then possibly 5, the quantum gravity models that we'll get into. So yeah, that is aspect number 1 right there. And as I said, so I think aspect number 1 has been proven beyond reasonable doubt. I assigned a subjective probability of 99.95% proven from the evidence of the second law of thermodynamics and the spatial expansion of the universe, alongside with the mathematical singularity theorems and proofs, that yes, the universe is in fact does have these thermodynamic properties, and in fact is expanding spatially. So that's spatial expansion, and that the spatial expansion indicates that the universe began to exist. So I'm not necessarily, it's associated with the expansion of the universe, and it indicates that the universe began to exist at face value. So this isn't saying that the universe actually did begin to exist. It's just saying, at face value, given these 2 data that we have, or categories of evidence, it does seem like the universe began to exist at face value. Okay, so now we're going to actually, okay, great. Now how do we assess the various cosmological models to see if the model that says the universe did in fact begin to exist is the best explanation of this data that we covered in aspect 1, versus other eternal cosmological models that also try to claim to explain these data and be consistent with these singularity theorems that we've given. So that's what we're going to be doing next, is getting into aspect 2. And the first thing I want to do here is lay out the non-eternal cosmological models. And on this front, I'm actually going to be giving just one. I'm going to be calling this the unspecified finite universe model. So I'm not necessarily even going to be arguing for the Big Bang model. I don't care if the Big Bang theory is true or not, and that sort of thing. I just care, my model only says that at some point in the finite past, 6,000 years ago, 13.8 billion years ago, whatever the heck you guys want to say, the universe began to exist. The when, the how, doesn't matter. I'm going to leave that unspecified for this model. So this is a very broad, generalized, and vague model, but it does make that specific prediction that it's unnegotiable. The universe did in fact begin to exist a finite time ago. So just to kind of lay out some of the details on this model now, I think it's actually kind of helpful to understand the Big Bang model, even though we're not dependent upon arguing for the truth of the Big Bang in particular. We're just arguing for an unspecified model that entails a beginning to the universe a finite time ago. It could help us to understand what an unspecified model might look like by understanding the traditional standard Big Bang model. So basically, the standard Big Bang model that was developed first in the early 1920s by Feynman and Lemaitre, and was confirmed observationally in 1929 by Edwin Hubble. As I said, as we learned about in aspect 1, almost overnight that became the accepted model for the origin of the cosmos or the universe. And it remained completely unchallenged until the late 1940s. Now, today in the 21st century, the Big Bang model, so the standard Big Bang model, the original version, has been falsified because there are certain problems that come up and needed to be corrected for. So we now have the modified Big Bang model. And this is by far the most widely held view among modern cosmologists, physicists, and astronomers. The strong majority view among scientists and experts is that the Big Bang is true. So if you're an atheist or a skeptic and you're going for the one of these modern eternal cosmological models, you're in the minority, my friend. We've got the scholarly consensus on our side. You've got a lot of, you got problems. You've got a lot of work to do to overcome the consensus view. Christians are the consensus in science right now on this question. And believe it or not, even radical atheists and skeptical scientists who support eternal cosmological models, they all admit this, that the best explanation is the Big Bang model, not eternal cosmological models. So, for example, in a debate, Dr. William Lane Craig debated the famous theoretical physicist Lawrence Krauss. And Lawrence Krauss, in the debate, himself admitted that, yes, the Big Bang is the best explanation. That's the more probable explanation given the data we have. The eternal cosmological models, which he was defending in the context of this debate. I mean, he's written books defending, yes, the universe is eternal, we don't have to worry about it. But he admits it's improbable given the scientific evidence that we have at this point. So Lawrence Krauss kind of goes for possibility, not probability. And that's a logical error. You can't just say, well, it's possible, therefore it is. No. So just quoting that little exchange. So Dr. Craig says, well, yes, look, he argues that all of the evidence shows that the universe had a beginning, and that in these models, and then Krauss interrupts him and says, well, I would agree with that. I would agree with that. All the evidence shows, let's look, let's accept that fact. And Craig's like, okay. And then Krauss continues, all the evidence suggests that our universe had a beginning. All of it. Not a single shred of scientific empirical evidence suggests that it is eternal. And Craig, kind of baffled, says, okay. And then Krauss continues to stick his foot in his mouth and says, but we don't know. That's what I keep telling you. Knowing and suspecting are two vastly different things. And then Craig quite wisely says, yes, I get that, Dr. Krauss. No one is trying to say that we know with absolute certainty, 100% proven fact, that the universe began to exist. That is a mischaracterization on your part. What we're arguing is that the premise is more probably that the universe began to exist is more probably true than false. And on that front, you're actually agreeing with me. And then Krauss says, yeah, but it's still possible. So yeah, he's committing this fallacy of not understanding that possibilities are not probabilities. And if you're following the experts, every single one in the entire world admits the best explanation, the more probable explanation, is the Big Bang model, that the universe began to exist on the evidence. And in fact, there is absolutely zero evidence that suggests the universe is eternal in the past. So just kind of explaining again the Big Bang model. So the Big Bang model is a general relativity-based theory, so it requires general relativity to be true to work. And it as I said, it postulates an expansion of space itself, not the material stuff within the universe. And it says as you travel back in time, at one point, all the matter and stuff was all compressed into a very small state, hot, dense, pressurized state. And that was the beginning of the universe. So it'll approach an infinite density, infinite heat, infinite pressurization, and that sort of thing. That's what scientists call the singularity point, meaning the universe cannot have existed prior to that moment eternally. Space and time itself must have come into existence at or before that moment of singularity. And they calculate that to be 13.82 billion years ago. Meaning, again, that the time frames don't matter for us. We're open to young universe creationists, if you want to say it's 13.82 billion years or younger. So we can include whether you're an old universe or a young universe, you're included in this. But the Big Bang model in particular postulates no, it's the old version. It's 13.82 billion years. Yeah, as I said, so space expands just like that balloon. We gave the example of the balloon with buttons glued onto it. So the buttons represent the galaxies, the balloon represents space itself, and the buttons are stationary. It's the universe, it's the balloon that's blowing up, space itself that is expanding here. And a good way to represent this, just on an two-dimensionally on an XY scale. So you can have time as the y-axis and space as the x-axis. The Big Bang model looks like a cone, an upside down, an ice cream cone. So it starts at the singularity point of the cone, and then it expands upwards, gets bigger, bigger, bigger throughout time, and that sort of thing. And that's sort of the standard Big Bang model. With the modified Big Bang model, it's not necessarily a straight cone because the universe's expansion rate is accelerating. So it's kind of like it gets really, really fatter, quicker and quicker as you climb up the cone there. And another thing that needs to be mentioned here that wasn't accounted for in the standard Big Bang model, but does need to be accounted for, is the quantum gravity regime, because now we understand that there does have to be a phase of the universe where it was so small as it contracts back in time, it would have been in this quantum gravity regime, and therefore would have been governed by some yet to be discovered quantum theory of gravity. So that's something that's has to be accounted for in the modified Big Bang theory and wasn't accounted for in the standard Big Bang theory that we had starting from the 1920s. So that's something to be aware of. And yeah, as I said, with the BVG theorem, that shows that either classical space-time began with this past boundary, the singularity, or there was a quantum gravity regime. And that quantum gravity regime itself would represent the beginning of the universe. So it wouldn't go down straight to the point of the cone. It would go down only so far and then just at the quantum gravity regime, and then that's the beginning. It began at that sort of state as kind of like a cutoff cone with the point cut off at the bottom. Now, one final note that we kind of mentioned quickly in aspect one, another modification that needs to be made to any standard Big Bang theory is you'll probably have to include some notion of inflationary theory that goes back to Dr. Alan Guth back in the 80s. Some kind of notion of a super rapid inflationary expansion rate very early in the history of the universe, and at which point it stopped and went back to normal accelerated expansion as we see it today. So those are the three elements that in any model of the universe beginning at a certain point, based on GTR and the following along in the Big Bang model, it will have to be modified from the standard Big Bang model to account for these three elements. The fact that the universe's expansion rate is not just expanding, it's expanding at an accelerated rate. There's also, and it has to include some kind of inflation period very early in the history of the universe. And finally, there is a quantum gravity regime where that would have to constitute the beginning of the universe, because GTR does not take you all the way down to a singularity point. At a certain point, the universe is small enough that the quantum gravity regime applies, and you need some quantum gravity theory or theory of gravity. Yeah, I think that's it in terms of understanding the Big Bang theory. And again, understand that we are not dependent upon the Big Bang theory, whether the standard Big Bang or the modified Big Bang as we have it today in the 21st century being true. All that ultimately matters is that, based on the data, this model is positing there was a beginning, a finite time ago in the past, to the universe as a whole, from which it started expanding, and that's all we care about. We don't care about the when or the how so much. Now, in terms of assessing this model, so I think it's the unspecified model, finite universe model. It obviously covers all of the bases in terms of the best explanation inference criteria. It's got great plausibility. It fits all of the facts. The notion that the universe began to exist at some finite point in the past, it's perfectly plausible as a concept. It's one that has existed for thousands of years, biblical Christians and that sort of thing. And in fact, the majority of the people on the planet today, both laymen and scientists, believe it's probably true. It's consistent with our modal intuitions from our properly basic beliefs caused by our modal evaluating faculties that says, yeah, it's very plausible that our universe could have begun to exist. Now, one sort of objection on the plausibility criterion that atheists and skeptics might try to raise here is they'll say, yeah, but the creation of the universe is an entirely unique event in history. It only happened once, so far as we know, and thus it's therefore highly implausible from a frequentist perspective. No one's ever able to reproduce the Big Bang in a lab or have it happen again in nature to assess the model's plausibility statistically, right? But this is just flawed reasoning on the part of the skeptic, because obviously unique historical events happen all the time. They're not repeatable. History is not repeatable in the same way operational science is. By the way, neither is forensic science. We have tons of examples in science of things that didn't happen. The extinction of the dinosaurs, that only happened once. I guess that's implausible then. This is just a flaw in atheist reasoning. Most scientists, whether they're atheists, they wouldn't say something so foolish, but we do have lay skeptics, and they often say or go for foolish types of objections. So I just wanted to raise that. Now, another more common atheistic argument against the plausibility of the universe beginning to exist a finite time ago is that this model posits the coming into being of space and time and all of its material contents from literally nothing. It entails a creatio ex nihilo, and that's illogical to them, and it violates naturalism. So in the first place, it's actually wrong. So the universe came into existence with God, from God. God was the cause of the universe. Now, he wasn't the material cause, but you don't have to have a material cause. He was the final cause. If that's the case, then it is plausible to imagine the possibility of the universe coming into being without space and time or material contents existing eternally. We'll get more into that later on. That's more of an objection to other premises, but just wanted to mention that here. And they also say it violates naturalism. Well, naturalism is just a biased worldview without any proof. Atheists and skeptics just kind of blindly believe it as a religious faith belief or proclamation. They have no, or rather irreligious belief, but they have no actual proof. So you can't establish the implausibility of something based on a biased, unproven worldview. Asserting and assuming is great, but that proves nothing. So in order to prove that the Big Bang Theory or the unspecified finite universe model is implausible, the skeptic would have to prove that naturalism is in fact true, not just assert it's true. And of course, they utterly fail on that in that regard. So this objection doesn't work. So yeah, I think it's 100% proven that the Big Bang model, and or whether standard or modified, and or just this unspecified finite universe model that we're arguing for here, 100% proven that is plausible and it fulfills the plausibility criterion. What about explanatory scope? Well, this model explains every single fact that we have, and going hand in hand. So it covers Friedmann-Lemaitre equations, it covers the redshift, it covers the light element abundance, it covers and explains the CMB radiation, and it covers the modern singularity theorems perfectly without any effort or vagaries, so therefore it automatically has both explanatory power and explanatory scope. One thing I will say on the part of atheists and skeptics in terms of explanatory power, though, is that it is true in the field of cosmology that it's not a fully developed field yet. It is something that's, we're progressing beyond. We're not in its infancy anymore, but, we're not fully baked. It's not a field that's fully baked yet. There are still lots of mystery factors that cosmologists are still working on, trying to work out and understand. Just for example, dark matter, dark energy are things that we know very little about. Inflationary theory, which is something that is required, there are mysteries there. And of course, we just have no clue as to a theory about of quantum gravity. Yeah, it has to be admitted that there are gaps in our knowledge in this field. And this uncertainty may be seen to kind of say that some kind of unspecified, eternal cosmological model could fill in these gaps and fit in despite the unspecified finite cosmological model of the universe fitting all of the seeming to fulfill explanatory power, scope, and all that. Maybe we're wrong about the levels, saying that it actually fulfills these criteria because of our infancy. We have insufficient knowledge of the field of cosmology at this point now, and that may allow us to fit in some kind of unspecified eternal cosmological model. Well, I'm going to reject that right away. I think that our knowledge is in its infancy and there are gaps in our knowledge, but it is probably sufficient to allow us to say, yes, the unspecified finite cosmological model that we're arguing for here, I'm at least 70% certain that we know enough to say, yes, it does fulfill these criteria. And you can't just appeal to the fact that there are mystery factors to say that we don't know and that sort of thing, and thereby smuggle in some kind of unspecified eternal cosmological model as a counter and say, well, maybe the unspecified eternal cosmological model is the better explanation compared to the unspecified finite universe model that you're giving us here. No, we know enough about the field of cosmology to, at least in my subjective opinion, I think that I'm at least 70% convinced that no, that's not the case. We know enough to know, yes, these models do fulfill the criteria. Sorry, the unspecified finite model does fulfill these criteria, and specifically the explanatory power criterion that we're talking about here. So, given this current state, I'm only going to assign a 70% to 75% proven fulfilled for the explanatory power criterion with this unspecified finite universe model, just out of deference for the fact that there is mystery there. I want to give at least a 30% chance that this mystery appeal might mean that the unspecified finite universe could lack sufficient explanatory power in some. And finally, in terms of less ad hoc or simplicity, 100% proven here. There are no specified unproven claims in this minimalist model. There are some with the Big Bang model, perhaps, or that sort of thing, but because we're going with this minimalist, unspecified finite universe that only proposes, hey, the universe began to exist at some finite point in the past. That's it. That's what the model is. It doesn't matter when, 6,000 years ago, 13 billion years ago, we don't care how it happened, that sort of thing. So yeah, this is 100% proven. It doesn't incorporate any unproven claims or assumptions in order to work in explaining the data. So yeah, so all in all, based on the 4 inference criteria, the unspecified finite universe model gets 100% on plausibility times 100% on explanatory scope times 70% for explanatory power times 100% fulfilled on the less ad hoc or simplicity criterion. Therefore, there's a total 70% proven chance, 70% proven that the unspecified finite universe model fulfills all 4 of the best explanation inference criteria. Now, just as an edit on what I said there, so the unspecified finite model also entails things that relate to the facts in aspect 1. There's spatial expansion. The universe is spatially expanding from a very hot, very dense, very pressurized state. So that's also included there in this model. As well, it had went through an inflationary phase very early in its history of super rapid inflation. It may or may not have included a quantum gravity regime in its earliest phase as it's beginning to the universe. And of course, the expansion rate of the universe is accelerating. So all of these facts are also included in our unspecified finite cosmological model that we're giving. So that needs to be said as well, in addition to the fact that it began to exist a finite time ago. Yeah, that's my take on that. Next, let's start looking at the contrary. Okay, great. We've got the model that posits the universe began to exist. We understand how that relates to these four best inference criteria. What about the specified eternal cosmological models? Eternal cosmological models, models that posit the universe existing for all eternity in the past, but the ones that they're specified, because we already dealt with the unspecified eternal cosmological model in the explanatory power of the finite model that we gave there. So now we need to compare the unspecified finite model after defeating the unspecified eternal model and take a look at some of the specified eternal cosmological models, the specific models that we actually have been proposed to date, and see how they compare to the unspecified finite cosmological model. So let's start looking at some of those for the compare and contrast. And the first one up on that list, the first eternal cosmological model to look up, is the one that came about chronologically first, the standard steady state, as well as the updated quasi steady state cosmological model. So let's take a look at these models here. Okay, so Sir Fred Hoyle was a famous scientist of the 20th century. And he was an atheist, and he was very desperate to avoid the obvious truth that God exists and that the universe began to exist, basically just out of pure skeptical bias on his part. And so what he did, in 1948, he came up with the first modern eternal cosmological model. So the first model that posited the universe might be eternal after the revolutionary discovery that the eternal static model of the universe is scientifically falsified and impossible to be true. In light of GTR and the equations and Edwin Hubble's and that, so discovery of the redshift data and that sort of thing. So in 1948, Fred Hoyle was quite desperate because he felt his atheism was under threat. So what he did was come up with a new modern eternal cosmological model called the standard steady state model, or just the steady state model for short. And essentially what this model posits is that, okay, so absolutely, it's a scientifically proven fact that the universe is expanding. Cannot deny it. You're an utter ignorant fool if you do deny it. So great, the universe is expanding, but it's still eternal in the past because in the center of the universe or whatever, there's this there was no center of the universe, but the universe is constantly, continuously creating new matter to replace the matter as it goes out and that sort of thing. So the matter density of the universe is maintained at a constant level through this made up notion where he just says, well, matter is just created ex nihilo out of nothing for no reason at all, continuously throughout history, over billions and billions of years, throughout eternity itself. And this was called the steady state model and that sort of thing. And we'll get to assessment. Obviously, you can see right away it violates the laws of thermodynamics, but we'll get to that in the assessment portion. But yeah, you'll see on the screen what this model entails. You'll see continuous ex nihilo creation of new matter to replace the old matter that's constantly expanding away and that sort of thing. Now, as we'll see, this model was there's no evidence for this model. It was nothing but sheer skeptical bias on the part of Fred Hoyle that caused him to assert and assume that this was what was going on. And as we'll find out, every scientist in the world today laughs at anyone who thinks this steady state model is true. The most biased atheists in the world say you're an utter fool if you think that this is correct, and that's including Fred Hoyle himself. His model, as we'll find out, has been scientifically falsified. Impossible for it to be true. So obviously Fred Hoyle, as I mentioned, was extremely biased as an atheist, and he hated this. He hated the fact that the Big Bang model was proving Christians were right this whole time, and that the universe did begin to exist, therefore God. So what he did in 1993 and 1994, he and a couple of other scientists attempted to revamp the old discredited steady state model. And this resulted in a book. They co-authored a book in 2000 called A Different Approach to Cosmology. And here they advocate for what's called the quasi steady state creation or quasi steady state cosmological model of the universe. And so this model, basically, just like with the original steady state model from 1948, it says that the universe has always existed eternally. But this time the universe is said to undergo pulsation, where it alternatively expands and contracts, and this bounce at the end of each collapsing stage is basically caused by some kind of field with a negative energy density. So it's kind of analogous to, on the Big Bang Theory, we have this notion of dark energy in it. So it's kind of this notion of negative energy density field is analogous to what dark energy is supposed to do on the standard Big Bang Theory. Now, this newer model obviously incorporates more of the observational evidence, so it fares much better than the 1948 one, which was falsified by subsequent scientific observations. And this accounts for that, for those types of things, for many of those types of things. But yeah, it's still utterly a failure, and we're about to just get into the assessment thing to find out why these models fail. But as you'll see on your screen, here's the visual image of the expanding, contracting pulsations or bounces on this new quasi steady state model. Okay, so let's get into an assessment of these two models in the light of the best explanation inference criteria. Okay, so on the first criterion, the criterion of plausibility, so that's again, is the model implied by, or at least consistent to a greater degree by a greater number of the other accepted truths of our background knowledge compared to other hypotheses. So in this respect, the steady state model is an utter failure, 0% chance that it's true in this case, or at the very least 99.99 if you want to be, show that science has its limits. But basically this model contradicts, it posits the creation ex nihilo of new matter and energy into the universe, and that's scientifically speaking impossible. It violates the first law of thermodynamics, those laws that are impossible to be wrong. That first law of thermodynamics being the law of conservation of energy. Energy can neither be created nor destroyed. It only can be changed or converted from one form of energy to another. So right away, bada boom, bada bing, the steady state model, complete rubbish. Throw it in the garbage. With the quasi-steady state model, I'm actually going to refrain from judging that based on plausibility, just because I'm not a scientist and I was unable to find information pertaining to the plausibility of it. So I'm going to assign it 100% proven, the quasi-steady state model from 1993 and 94, a 100% proven fulfilled on this plausibility feature. That's not because I think it is in fact plausible. It's just because I was unable to find any information pertaining to its plausibility that would be relevant, and I'm just an ignorant lay Christian. I'm not a scientist, so I would have no way of saying it's actually implausible. So because I had no sources that explained to me how it was implausible, I'm just going to give it a pass and say, yes, you fulfill this one. Now, in terms of the next criterion, explanatory scope. Now, in terms of the traditional 1948 steady state model, this model does have explanatory scope in terms of accounting for the general relativity, the Friedmann-Lemaitre equations. It also accounts for the observational redshift data that we got from the late 1920s, as it does postulate eternal expansion of space, and thus galaxies and objects will recede from us, and that create that redshift account. However, this model is inherently unable to account for the CMB radiation or the light element abundances. Remember that hydrogen and helium abundances, 98% of the matter. This model just can't explain it inherently. Impossible if it's true to explain these things. And of course, it's an utter failure on the mathematical singularity theorems or the mathematical proofs, like the Hawking-Penrose singularity theorem or the Borde-Vilenkin-Guth or BVG singularity theorems. Utter failure. This model is 0% that the steady state model has explanatory power in this regard. Now with the updated quasi-steady state model, obviously this does account or attempt to account for more of the observational evidence. So it does account for the light element abundances, the CMB radiation. The thing that it lacks in terms of explanatory scope is it doesn't account for the 2003 BVG singularity theorem evidence at all. So therefore it lacks explanatory scope. I assign it about 4.99% proven fulfilled level that for the QCC has explanatory scope. So, it's proven beyond reasonable doubt that even the quasi-steady state model lacks explanatory scope, but it's still possible. I gave it a 4.99% probability that it does fulfill the explanatory scope despite not addressing the BVG singularity theorem at all. It came out before that was published. So, okay, next, the most important one is explanatory power. Does the model explain the data with the least amount of effort, vagueness, or ambiguity? Well, the steady state model is entirely inconsistent and contradictory with the observational evidences of the light element abundances, which could not possibly, it's not even possible, to have formed through stellar nucleosynthesis, given the truth of this model. And, we also have that cosmic microwave background radiation discovered in 1965. So this has been said by scientists to, quote-unquote, put the nails in the coffin of the old steady-state model, which couldn't, inherently, impossible on its own grounds, impossible for it to explain why this background radiation was there at all. The reason for this is because the quote-unquote universe now is producing a black body since it is not isothermal and it is not transparent instead of opaque. In the steady state theory of the universe, it was always the same, so it never produced a black body. We have the CMB that is a black body, bada boom, you're done, quote-unquote, hence the existence of a black body background ruled out the steady state. 0% proven on the explanatory power. What about with the quasi-steady state creation model from the mid-90s? Well, this model is also an utter failure, despite its attempt to account for more of the observational evidence compared to this traditional 1948 steady state model, but it just doesn't do so. So look, in the first place, it is contradictory and inconsistent with the BVG singularity theorem. Also, the new QSSC model or quasi-steady state model fails to account for the abundance of the light elements, so it attempts to do so. So it has explanatory scope, but it's just an utter failure. It doesn't have the explanatory power to explain the light element abundances. Here's a quote from scientists. So, quote unquote, the nucleosynthesis theory in the QSSC model leading to the standard helium abundance is frozen in the 1960s. It utterly cannot do so, account for this data. What's more, the new QCC's model, or quasi-steady state model, claims to fit or account for the CMB anisotropy data. Remember, the CMB radiation is remarkably isotropic or uniform throughout, but there are some anisotropies in there. The quasi-steady state model utterly fails to account for these anisotropies that we find because, quote-unquote, their model does not fit the WMAP 3-year data, nor does it fit the CBI and ACBAR data that were already published. It is very clear that the quasi-steady state CMB angular power spectrum model proposed does not fit the CMB data. And that's a direct quote from some world expert, Edward L. Wright, and he's written his article, Errors in the Steady State in Quasi-SSS Models, and you have the link for free. You can read his explanation of that. So on this front, both models, utter failures, 0% probability that the steady state fulfills the explanatory power, 0% probability that the quasi-steady state modification models account for fulfill explanatory power on this front. So Finally, we go to the less ad hoc criterion, or the simplicity criterion. And in this front, the steady state model is extremely ad hoc. It involves many non-evidenced assumptions, major. It was created solely to account for the 1929 redshift observations in order to preserve an eternal universe, just to satisfy the desperate atheistic desires of the biased scientist Fred Hoyle, who was afraid of believing in God and admitting the truth that the universe did in fact exist. So, also it's extremely ad hoc to posit the notion of new matter and energy would just continuously be created constantly over eternity as the galaxies receded away from each other. It's completely non-evidence. There's no understanding of any kind of mechanism that would be at play to do this. So utter failure, 0% on this. If you want to be generous, you can give them 5%. I gave them 5%. Proven fulfilled for the standard steady state. That's just me being generous. Now the quasi steady state model, believe it or not, it's actually worse than the original steady state model in this regard, because in addition to all of the it also posits an ad hoc element in trying to account for the most recent CMB data as the motivation for the model. So it's the entire model is ad hoc itself, but then on top of that, they make poorly justified changes to fit into the 2003 version of this model, just for the purpose of fitting the most recent CMB data, and it employs non-proven assumptions or non-evidenced assumptions that are just contradicted by the model's predictions itself. So 1% proven on this, utter failure. So yeah, in total, in terms of looking at the traditional or standard steady state model from 1948, for all four, there's a 0% proven factor that this eternal cosmological model fulfills all four of the explanatory criteria, at best explanation inference criteria. And there's also a 0% probability when you multiply it all out, 0.01% or 100% assumed times 4.99% proven for the explanatory scope, times 1% for the less ad hoc, times 0% for the explanatory power. So there's a 0% probability that the quasi-steady state model fulfills all four of these criteria for being the best explanation. So yeah, these are total failures. I think with that said, let's move on to the next modern specified eternal cosmological model, and this is the eternal quote-unquote oscillating big bounce cosmological models, very popular by hippies and Eastern religions like Hinduism, Buddhism. They like to appeal to this kind of thing. So yeah, let's get into that. What are these oscillating or big bounce cosmological models that purport to be eternal in the past? Well, essentially what they postulate, again, these were popular back in the 1960s and possibly early 1970s. Again, you can see the image on the screen. But these were mostly propagated by Eastern religious people or by atheists and communists, Russian cosmologists and scientists. And they basically speculated that, well, if they denied the homogeneity and isotropy of the universe as a whole, therefore they could sort of postulate by doing that the internal gravitational pull of all the mass of the universe might actually be able to overcome the force of its current expansion, halt that expansion, and then actually reverse it so that it entered a big cosmic contraction phase. So the universe expands, slows down, all of a sudden, boom, stops and starts contracting. And this was called the Big Crunch. So basically they say, well, if this were the case, then the collapsing universe might not coalesce at a singularity point, therefore proving there has to be a beginning of the universe. But instead, maybe the material contents of the universe, as they're contracting, they might move past each other so that, okay, well then the universe would appear to bounce from before getting to the point, it gets really, really, really small, and then boing, bounces and it starts expanding again. And this was known as the quote-unquote big bounce eternal cosmological model. And so the idea is, look, the universe throughout all of eternity has gone through these contraction, expansion phases, and we just so happen in the 20th century to be observing the universe in one of its eternal expansion phases that it's been going throughout all of eternity. So that's what this oscillating model or big bounce cosmological model is. Now let's get into some assessments. So in terms of the plausibility, is this model implied by or consistent with other accepted truths given our background knowledge? No, it's an utter failure, because these models oscillating big bounce models are extremely implausible. So in the first place, there is absolutely no known physics in the world that could even theoretically allow or cause a collapsing, contracting universe to quote unquote bounce back into some kind of new expansion phase. There's just nothing we know of or can even conceive of theoretically that would serve as a mechanism to do that sort of thing. But what's even worse for this model is we have observational, scientific, empirical evidence that proves that the mean mass density of the universe is insufficient to generate enough gravitational attraction to ever halt and then reverse the current expansion of our universe. Remember, we're in the expansion phase. It's just utterly implausible that we could ever revert to a collapsing or contraction stage, given what we see about the expansion of the universe today. There's just insufficient a mean mass density to generate that gravitational attraction to cause us to go into a contraction phase. Therefore, impossible, could not have been eternal in the past. And just kind of going further, in 1998, astronomical teams from Princeton, Yale, Lawrence Berkeley, and Harvard-Smithsonian Astrophysics Institute all reported that various scientific tests all confirmed with a 95% degree of certainty that the universe will quote-unquote expand forever. The density of matter is insufficient to halt the expansion of the universe. So utter failure, atheists. I'm sorry, you can't go for this big bounce model. Based on the basis that they said they're 95% degree of certainty, I was generous to the skeptic. It should be 0% proven on this for these models with plausibility. I assigned a 5% proven, just going with, well, there's a 95% degree certainty based on those 1998 data about the mean mass density of the universe. Okay, so next we have explanatory scope. What's the quantity of the facts that we learned about in aspect 1 that can be accounted for on this oscillating model? Well, the traditional oscillation models of the 1960s and early 1970s, they were obviously able to account for the redshift data. They could also account for the light element abundance, the hydrogen and helium abundance, and the CMB radiation observations at the time. But they all failed entirely to account for the Hawking-Penrose singularity theorem of 1970, and obviously the subsequent BVG or Bohr, Vilenkin, and Guth 2003 singularity theorem. And that applied regardless whether the universe was homogeneous or isotropic or not. So yeah, the isolating models are inherently, by definition, logically contradictory to these mathematical proofs. Hawking and Penrose destroyed the oscillation models. You cannot believe that those are true, given we've mathematically proven the Hawking-Penrose singularity theorem and the BVG singularity theorem. Believe it or not, it was the recognition of the Hawking-Penrose singularity theorems that really led to the total abandonment of all attempts to argue for a previous contracting phase in the universe's past history. It also led to us discarding notions about a non-singular big bounce from contraction back, boing, bounce into expansion. We got rid of that. A singularity, assuming the truth of the 5 generalized conditions of the Hawking-Penrose singularity theorem there, it was proven to be inevitable. You cannot escape it. So utter failure, 0% proven fulfilled level on explanatory scope for oscillation models, eternal oscillation models. What about explanatory power? What is the quality of this model in explaining all of the relevant facts we learned about in aspect 1? Well, like I said, they were able to relatively well explain the redshift observational data as it was known during the 1960s and early 70s. Unfortunately, more recent findings after the 1960s and early 70s actually made any question of the density of matter in the universe that is required on the truth of this model. Remember, in order, as we learned about in the plausibility, to get that contraction phase, we have 95% degree of certainty that we just don't have the mean density of matter sufficient to initiate that contraction phase of the universe. And yeah, basically, more recent findings have made this wholly mute, as the redshift data from distant supernovae has now shown that far from the universe's expansion decelerating, as one might expect given the oscillation cosmological model, it expands, slows down, stops, and then contracts, and that sort of thing. No, it's the exact opposite. We learned from aspect one that the expansion of the universe, it's actually accelerating. The expansion rate of the universe is accelerating. It's getting bigger and bigger, faster and faster, exponentially. And I have a quote in my book from NASA just confirming that. I think that's good enough. I don't need to read that quote, but yeah. Well, actually, you know what? Yeah, I'll quote NASA here. So, quote unquote, if the density of the universe is less than the critical density, which is proportional to the square of the Hubble constant, then the universe will expand forever. If the density of the universe is greater than the critical density, then gravity will eventually win and the universe will collapse back in on itself, i.e. the so-called Big Crunch. However, the results of the WMAP mission and observations of distant supernovae have suggested that the expansion of the universe is actually accelerating, which implies the existence of a form of matter with a strong negative pressure, such as the cosmological constant, and this strange form of matter is also sometimes referred to as dark energy. If dark energy in fact plays a significant role in the evolution of our universe, then in all likelihood the universe will expand forever. So that's the quote from them. Now additionally, on the explanatory power criterion, we kind of mentioned, so it utterly fails, and it in fact is contradictory with the truth of the BVG and Hawking-Penrose singularity theorems. So these two facts from aspect one alone completely rule out the eternal oscillation or big bounce cosmological models. The universe must shrink down to a singularity point. It's inevitable as you travel back in time. Okay, also, oscillation models also fail to adequately account for the CMB radiation that we learned about in aspect one. So, it's basically been discovered this CMB radiation is remarkably homogeneous or isotropic in every single direction, 1 part in 100,000. So if the universe were the result of some kind of prior oscillation, as this eternal cosmological model says, well, then scientifically speaking, we know that a contracting phase would have created all sorts of black holes. It would have created various density perturbations that then would have been reflected in this CMB radiation. In this would always be caught when it's expanding or contracting over eternity. These kind of black holes and density perturbations would always be preserved and reflected in the CMB or cosmic microwave background radiation in whatever subsequent expansion phase came about. So yeah, a contracting universe would just be filled with black holes and other objects formed by gravitational self-collapse. What's the problem here, observationally? Well, we just don't find any such features in the CMB evidence, and therefore it's scientifically impossible for such features to be smoothed out when the universe started its post-expansion phase. So this is a really big deal that disproves that the eternal oscillation models have explanatory power. But finally, we have a major difficulty with these oscillation models in accounting for the thermodynamic properties of the universe in light of the second law of thermodynamics that we learned about again in aspect one. And basically, the problem comes in because, look, entropy, entropy or this disorder isn't conserved. It can't pass through a singularity point. The problem, and that's sort of if somebody wants to say, well, there you go. There's not a problem of a buildup of entropy in the universe or a buildup of disorder that accumulates from cycle to cycle as you're expanding and contracting, and that sort of thing. It just can't pass through that singularity point. But the problem is, well, neither can anything else. And that's why the proponents of the oscillation model say, well, it doesn't go through a singularity. It bounces back before it gets to that point. But once you say that, Mr. Atheist and Skeptic, you're in for a world of hurt. Because, well, then the entropy of the universe is also conserved. It doesn't get eliminated because it doesn't go down to a singularity. It's conserved through each bounce. And what happened in the mid-20th century, the American mathematical physicist and physical chemist Dr. Richard Tolman, he demonstrated conclusively that in this kind of circumstance, the entropy is in fact conserved and accumulates from cycle to cycle. Again, expanding, contracting. And as a result, all oscillating models have the undesired effect of basically generating an increasingly larger cosmic scale and a longer temporal duration for each successive cycle of oscillation. So instead of the image that I showed you before, what you get is this kind of thing where each expansion phase, the universe, after it bounces, it expands longer than last time. And bigger than last time, and then it contracts, then it expands even longer and even bigger, and so on and so forth out to infinity. And this has certain implications for the eternality of this model. So consequently, astronomer Joseph Silk, he's used the known current level of total entropy in the universe that we have as we see it today, and he's proved that even if we just concede that these oscillations or these big bounces have in fact occurred, which, as we saw above, it's impossible for them to do that. Even if we just say magic did it and it happened, the universe could only ever have gone through no more than 100 previous oscillations. And therefore, an absolute beginning of the universe in the finite past is again entailed by these models. Now, believe it or not, it gets even worse for these oscillation models based on the thermodynamic properties of the universe. Because under eternal oscillation models, they would actually require an infinitely precise fine-tuning of the initial conditions of the universe in order to work. So, for example, if the entropy, or aka disorder of the universe, is supposed to increase during the contraction phase, then this would actually be inconsistent with the scientific evidence that we have regarding the extremely low entropy condition of our own early universe within this expansion, quote-unquote expansion phase, as you want to call it. No, the entropy was extremely low. But that's the opposite of what an oscillation model would be after an eternity or of prior contracting phases, contracting expansion. And if we just bounced out of a contraction phase, we would have a high entropy condition in our early universe. That's not what the scientific evidence proves is the case. So yeah, I assign a 0% proven filled for all oscillation models of this type. They have zero explanatory powers, so utter failure for the atheists and skeptics on this. Now, in terms of the final best explanation inference criterion, the less ad hoc or simplicity for the oscillation models, I don't need it, so I didn't bother doing an assessment of that. I just skipped over it. On the basis of the explanatory power, scope, and implausibility, we already know that this model is an utter failure. All oscillation models have a total probability of fulfilling the best explanation inference criteria, or the BEI criteria, 0% proven. So we have 5%, generous 5% proven for the plausibility condition fulfilled, times 0% for the explanatory scope condition fulfilled, times 0% for the explanatory power condition fulfilled. Therefore, that equals 0% proven fulfilled that these oscillation or big bounce eternal cosmological models fulfill the 4 best explanation inference criteria as we're looking at it. So yeah, with that said, let's move on to the next, and this will be the last for part 3a. This will be the last eternal cosmological model that we'll look at. So this is the eternal closed time-like curves, or CTC, cosmological model. And you'll remember, as we noted in 1970, in aspect 1, we have that Hawking-Penrose singularity theorem. And that theorem proves mathematically, absolutely conclusively, that the universe must have began to exist at a singularity so long as those 5 conditions are satisfied. And as we saw when we covered this in aspect, as we covered this before, 2 of those are automatically dismissed as being proven satisfied beyond reasonable doubt. So we skipped that, and we went with Dr. Stephen Hawking, who said that it's been proven there are only 3 possible exceptions to the Hawking-Penrose singularity theorem that might allow for a past eternal universe. And this is the first of those 3, the postulating a closed time-like curve cosmological model, where the universe kind of acts like a time machine, a closed time loop, where the future becomes the universe's own past and causes the universe to come into existence. So that's where this model fits in here. And just to give you some background, so the model we're looking at here, as you can see on your screen, back in 1997, 1998, doctors Richard Gott and Li proposed an eternal cosmological model in which only the earliest phase of our universe involved this kind of closed time-like curve. So you can see that in the picture at the bottom there, which is allowed by general relativity, and that is what ultimately gave birth to our universe. So the universe is literally the cause of itself of coming into being, or coming into existence. Its future traveled back in time and gave birth to itself as its own mother, type of thing, which is really weird for most people, common people, to wrap their heads around. But yeah, in this way, that the circular causation that's postulated through time travel here is what allows this model to avoid the problem of the universe. And so it does this through quote-unquote quantum tunneling. But instead of saying, well, it quantum tunneled into existence from nothing, well, they say, no, it quantum tunneled into existence and expansion from a previous state, namely its own time-traveling self. So at face value, that gives it kind of a leg up, you would think, compared to other models. So yeah, basically, instead of saying, well, the universe beginning at a singularity point, like that ice cream cone, the point of an ice cream cone, like we saw with the Big Bang model, no, here its past boundary is none other than a closed time-like curve. That's what's at the bottom, at the beginning of space and time and that sort of thing. So yeah, just showing you a couple images of how it works there. But it's important to note that the model posits that this CTC, or closed time-like curve region, is separated from the future evolution of the universe as we see it today, in expanding today. And this gets confusing. So this closed time-like curve region is separated from us today. It's separated by what's called a Cauchy horizon. What the heck is a Cauchy horizon, you're asking? Basically, it's just a hypothetical boundary that separates space-time into a CTC and a non-CTC region, or a closed time-like curve and a non-closed time curve region. And then obviously once it's separated from that CTC region, well, then the various branches in the above images represent kind of a multiple inflationary universe, or a multiverse, where with multiple expanding universe bubbles kind of going through expansion as per inflationary multiverse theory would predict. So that's what the model is in a nutshell. And as I said, yeah, you can see the image. If you're watching this on the YouTube video version of the show, then you'll be able to see it with your own eyes, so to speak. So yeah, with that said, let's get into assessing this closed time-like curve, or the Gott-Li cosmological model of the universe that purports to be eternal in the past. So in terms of plausibility, the Gott-Li, or the CTC cosmological model, in the first place, it is dependent on the truth of the B theory of time. Time travel is impossible to be true on the A theory of time. And remember, in part 2, we proved that it was our subjective probability, 82% proven that the A theory of time was true. So if you personally think that the A theory of time is true, given your background knowledge, then automatically this model is falsified. It cannot be true unless the B theory of time is true. And by the way, it doesn't even have to be an A theory of time. If you're a proponent of possibilism, which is kind of like a hybrid AB, where there's the eternal past exists, but not the eternal future, game over for this model. It only works if the B theory or eternalism theory of time is in fact true. Now remember, we said though at the beginning of this argument, for our own abductive argument here in parts 3a and 3b, this is a time theory independent argument. So I'm not going to assume that the A theory of time is true or something like that. We can assume for the sake of argument that the B theory of time is true, in which case this model is plausible. But I just wanted to point out that this potentially could be an objection against this model if you listening to the show have warrant like I do to know that the B theory of time is false, and therefore you can reject this model as being implausible on those grounds. Okay, so explanatory scope. So this model does do well. As I said, it was invented as an exception to the Hawking-Penrose singularity theorem itself in the late 1990s. It does not explicitly address the 2003 BVG singularity theorem, but the theorem applies to that theorem applies to classical spacetime, and this model applies in the quantum realm, not in classical spacetime. So I'm reasonably sure that this model can accommodate and account for even the 2003 BVG singularity theorem, or at least it can speak to it, even though chronologically speaking it didn't have an opportunity to explicitly talk about it. It's implied it could handle it after the fact. So I just assume 100% proven that this model has explanatory scope. Now, explanatory power. Essentially, the number one objection against any time-like curve model, and that especially applies to the best of them, which is the Gott-Li model we're looking at here, is what Dr. Stephen Hawking called the chronology protection conjecture problem, or CPC problem. This is basically where all CTC models, including Gott and Li's that we're looking at right here, must have this separated CTC region. And that region itself must be in some kind of pure vacuum state of some kind. So it contains no real particles, no Hawking radiation, no inflationary bubbles or bubble universes. If any of that happens, if even the smallest amount of stray radiation occurs, and it would inevitably compound over eternity of going in that time-like loop and accumulate and compound to the point where it would become infinitely strong, thereby destroying the closed time-like curve loop and produce a singularity. Bada boom, bada bing, you're back to the Hawking-Penrose singularity theorem, and the universe must have begun to exist at some finite point in the past. So this is the number one objection to the explanatory power of these CTC models. And of course, Gott and Li were well aware of this problem when they came up with their model, and they do propose a solution to it based on the fact that quantum gravity is potentially able to provide several loopholes to this chronology protection issue, as it's called. So for example, there are quantum vacuum states that do not inevitably blow up on this Cauchy horizon. And Gott and Li, in their model, they postulate some kind of special initial state for the universe, one with absolute zero temperature, so that's 0 degrees Kelvin, of empty space that is called the quote-unquote adapted Rindler vacuum state. So this is a specific notion within the field of quantum gravity regime, and it's a very highly fine-tuned state. It's specially designed and precisely balanced so as to avoid this CPC problem, or chronology protection conjecture problem that we've listed here. Now, in response to this, Dr. William Hiscock has published a paper, and again, all of the scientific papers, if you go into my blog site and click on the cosmological argument, my write-up, my 200-page write-up as it's progressing, all in the footnotes, free links. You can read all of these scientific papers for yourself to get a more detail on what I'm saying here. But yeah, Hiscock, he's published a paper where he's arguing that the CPC, or this chronology protection conjecture, should be reestablished as applying to Gott and Li's model specifically because of a couple of reasons. So the first place is that, well, the initial conditions required for this model to be true, as we noted here, they're highly fine-tuned and therefore highly improbable to occur. That, their vacuum being of quote-unquote measure zero instead of all other possible Rindler vacuum states, or quantum Rindler vacuum states. Yeah, unfortunately for the Gott and Li here, and the atheists and skeptics who want to use this, the precise form of that the thermal fluctuations would need to be in order for this model to work are actually completely inconsistent with the Planck scale physics that are used by Gott and Li in their model. So believe it or not, this is highly technical stuff, so I know that a lot of you probably don't get it, but just understand here, Gott and Li propose certain Planck scale physics, and this logically contradicts the precise form of the thermal fluctuations that would be needed within this Rindler vacuum state of quote-unquote measure zero for it to work. So there's a logical contradiction in the model. It just can't happen. It's very, very extremely improbable at the very least. And secondly, Hiscock and others have also argued that the Zindler vacuum that's postulated by Gott and Li in this closed time-like curve model it's simply too unstable given more realistic physical force field. It requires an exact value for the identification scale for the multiple de Sitter state to obtain, for example. And once again, postulating that is inconsistent with the Heisenberg uncertainty principle of quantum mechanics. So, yeah, in summary, if the precise, it's called a quote-unquote Meissner identification scale, and if that's not entirely constant, then it will immediately destabilize and collapse. So this initial state that within the CTC, within this vacuum state that they're postulating, it's incredibly metastable or unstable, and it would almost immediately destabilize and collapse. There's no way that thing could have maintained itself over eternity. It's very, very improbable, according to the scientists, in the light of realistic physical force fields. So Gott and Li have to postulate unrealistic physical force fields and make ad hoc assumptions, as we'll see. But as we see, especially in light of the Heisenberg uncertainty principle of quantum mechanics, this model is just impossible to get off the ground, really. Now, Gott is aware of this, Dr. Gott, and he responds to this by saying that, well, the calculations showing this are based on a faulty Minkowski vacuum factor, rather than the Rindler vacuum that they use. The Rindler, they use a specific measure zero Rindler vacuum state. And Gott is trying to say, well, that avoids this stability issue that you're trying to bring in here. And he's kind of fudged the calculations so that it would exactly cancel out all the features, so that it would exactly arrive at this net zero stable vacuum and thereby avoid destabilization or avoid a collapse and prove that a beginning of the universe is necessary. One final issue on this explanatory power, it's related to the thermodynamic properties of the universe. So Dr. Aaron Wall says that this model violates the second law of thermodynamics. And Dr. Wall, a Christian physicist and brilliant person who we mentioned in aspect 1, and he basically says that the event horizon of the CTC region involves a certain level of entropy that would have to be proportional to the area of the event horizon. Now, obviously, if CTC is correct, then the area of the event horizon would be expected to decrease. And that in turn entails a decrease in the total level of entropy. This is sort of a similar objection to what we saw with the oscillation models. But that's contradictory to the second law of thermodynamics. Entropy will only ever increase. It cannot decrease within a closed system. And the CTC would qualify as being a closed system. So basically, Dr. Aaron Wall is saying, well, a closed time-like curve model, an eternal closed time-like curve model violates the second law of thermodynamics. On it, postulating it entails a decrease in the total level of entropy, but the second law of thermodynamics tells us that the total level of entropy within a closed system must always increase. It cannot decrease. So that's sort of the objection that Dr. Aaron Wall gives, and I give that sort of quotation. Once again, Gott and Lee, in fairness, Gott and Lee are aware of Aaron Wall's objection, and they respond to it. And they try to respond, well, they say our model is more like a cylindrical model. And as such, it simply is there isn't this area decrease in the event horizon that initiates this problem and entails an overall decrease in the total level of entropy. So yeah, basically Wall's argument is just not applicable to Gott and Lee's specific closed time-like curve model. And again, we've selected the Gott-Li model because that is the best of the CTCs as far as we can tell. So yeah, this objection, we can't prove that it does violate the second law of thermodynamics in the way that Wall argues. So that objection has a plausible answer that's equally possible. So yeah, given what we said, we looked at 4 objections, and I think that the last 2 do have plausible answers and that sort of thing. So I've assigned a 10% probability, even if they're improbable, to be true. So I've assigned a 10% probability for proven fulfilled on this explanatory power criterion. Again, most of that, it's because their state is incredibly fine-tuned, and that's just very unlikely to come about. Now, the final criterion here is the less ad hoc, or the criterion of simplicity. Now, this model, as we've seen from the explanatory power, is extremely ad hoc. In the first place, the initial conditions, as we saw when we discussed the explanatory power, the assumed initial conditions that are completely non-evidence for this model are highly fine-tuned. Their vacuum being a measure 0 in the set of all the other possible Rindler vacuum states that might have obtained. This just makes it extremely unlikely to be true. D.H. Kuhl, for example, he concurs that their model is, quote-unquote, rather contrived. And he adds that the nature of their postulated initial Rindler vacuum state entails that thermal fluctuations involved would be required to be of a highly precise form in order to avoid any of the radiation back reaction chain problem, or in other words, it's that chronology protection conjecture problem that we mentioned as the first problem in the explanatory power section above. Now it gets even worse, because this entire model as a whole is ad hoc. Given the truth of the B theory of time, even given the truth of the B theory of time, the entire model just becomes superfluous. I mean, the reason for this, it being superfluous, is because, think about it, on the B theory of time, the block universe, the eternalism model, well, the universe never truly comes into being in the first place. So it's just a whole 4-dimensional space-time manifold exists tenselessly and eternally, and it means that there is no need for this complicated notion of a causal loop or a closed time-like curve to begin with in explaining how the universe came into being. There was no beginning, there was no coming into being in the first place for the universe. It just always was, past, present, and future, in an eternal 4-dimensional block. So on that, if we're assuming the B theory, then it would just be far simpler to just drop the CTC feature of the universe entirely and just say, yeah, the universe existed as a 4-dimensional block, as it exists here in the expanding phase separated. There's no need for a CTC on the other side of a Cauchy horizon in the first place. So I assigned 1% proven fulfilled level on this one. This model is extremely ad hoc and it's very problematic and makes it very unlikely to be true. Okay, so what's our total then for this model? Okay, so we have, I assigned my own subjective probability of 18% proven for the plausibility criterion fulfilled. Again, that assumes that the B theory of time is false. Or to be generous to the skeptic, we can say 100% proven and just assume that the B theory of time is true, since I said at the start that my abductive argument here is going to be time theory independent. So 100% proven for plausibility, generous, but in reality, I would assign that 18% proven, given that in part 2 of my cosmological series, I proved that the A theory of time is true, not the B theory of time. Then we have times 100% proven fulfilled for the explanatory scope criterion, times 10% for the explanatory power criterion fulfilled, times 1% for the less ad hoc criterion. So yeah, so I gave a total 0.18% proven that all 4 of the best explanation inference criteria are fulfilled by this CTC, or closed time-like curve eternal cosmological model that's specified by Gott-Li, who are the best proponents of this particular model. So not sure if the math is correct. I might need to recalculate that, but let's assume it's correct. So yeah, this is the best that we've seen so far of all the specified eternal cosmological models. Remember, there is that unspecified eternal cosmological model where I gave it a 30% chance at the beginning. When I said the unspecified finite model, there's 70% probability that one fulfills all the best inference criteria. But of the specified eternal cosmological model, this one is the best that we have, but it's less than 1%. It's pathetic. It's no comparison to the 70% that we got with the unspecified finite cosmological model. So for the atheists and skeptics are sucking big time. They're not doing a good job so far, but you know what? We haven't been fair to them in part 3A. I'm going to stop here, but in part 3B, we're going to get to the best eternal cosmological models that the atheists and skeptics of the modern 21st century have to desperately avoid the fact that the universe began to exist a finite time ago. And that's going to cover various eternal inflation models, eternal quantum vacuum fluctuation models, and that sort of thing, as well as quantum gravity models. So we'll get all into that in 3B. We're already over 3 hours. So that's it for 3A, part 3A of my cosmological arguments. As I said, in part 3B, that probably won't come out for several months. I'm in my new winter semester, and it's going to be really hard. There's a lot of work to do, so I probably won't even be able to look at this until spring, summer, and get something to you sometime in the summer, hopefully, to finish off 3B and part 4 and 5 of the cosmological argument. But yeah, the next thing up will be 3B, where I finish off the scientific cosmological model, eternal cosmological models, and show why I think the unspecified finite cosmological model is the best explanation, given these 4 best explanation inference criteria, compared to all the other eternal cosmological models, both the unspecified one we took care of here, and all the specified ones, some of which we covered here, the rest of which we will cover in part 3B. So yeah, that's it. With that said,